Powering on. Good afternoon, Dr. Asif. Good afternoon to all the participants.
Sixth day, in fact, the next week, second week of this course on NLP. I hope I'm audible to you.
Yes, sir. Good afternoon, sir.
The expert is already here, Dr. Asif Iqbal. By the time just introduced him. So Dr. Asif Iqbal, he is an associate professor in the Department of Computer Science and Engineering in IIT Patna, and he completed his PhD from Jabalpur University, and his thesis was studies on recognition, classification, and transliteration of Bengali named entities, a computational approach. He did his master's from Jabalpur University and bachelor's from Kalyani Government Engineering College. Dr. Asif has got so many fellowships, awards, and recognition. He received Japanese Society for Promotion of Science in 2017 to work as a visiting scientist in Kyoto University. Received Young Faculty Research Fellowship from METI, Government of India, Best Initiative Project Award from Indian National Academy of Engineering, and to name many more, so many such projects. He has done more than 20 projects from Ministry of Government of India and from private companies. Like his last project he is doing is imprint part 2 Sevak and sentiment analysis and image recognition from IMF Singapore, and then Indian language to English statistical machine translation from TDIL, METI, cross-platform, cross-lingual and multilingual event monitoring Indian languages from MHRD and METI, and so on. He has a lot of his work, most of his works are concentrated on NLP, and he has been actively, he is very actively participating in development of conversational chatbots and sentiment analysis and emotions in different the chatbot applications. So I would like to welcome Dr. Asif Iqbal. So Asif, voice is very low.
Hello, JP.
Yes, yes.
Can you hear me?
Yes, yes, I can hear you. I hope the participants are able to hear. Okay, so some have already confirmed that they are able to hear you. So Asif, I have already introduced.
Okay.
So the floor is yours. You can start.
Okay, okay. I'm starting.
I've already given you the permission for the presenter, so you can share your screen.
Okay. So
So, Dr. Asif, would you like should I allow the participants to interact you in between?
yes, yes. You can do.
Sometimes it might happen. Some of them it disturbs also. Some of them forgets to mute themselves, and a lot of noises also come. But I think we are here. We'll take care of that. So I'm allowing the participants so that they can interact with you as and when needed.
Yes, yes, yes. Sure, sure. Okay, so good afternoon to all of you, and thank you, Jyoti, for inviting me for this lecture. Mainly, I will talk about the conversational AI. And in conversational AI, particularly, I will be focusing on knowledge grounded and empathetic conversational AI. So I'll try to show the unimodality settings. That means where you have only the textual communications. And then if the time permits, I will also discuss about how in a multimodal setting, so where the communications can happen in different mediums, okay, so will be possible. Okay, here is the outline. So to begin with, I will briefly give a background to conversational AI. Then I will talk about the empathetic dialogue agents. That means how can we induce the sentiment, emotion, values in conversation. Then personalizations is important in conversation. Multimodal response generation is important. And then finally, the summary conclusions with a brief overview of what we are doing at IIT Patna in conversational AI. So the conversational AI is a, you can say, is a subfield of artificial intelligence. And you all know that AI these days is one of the most happening technology, discussed technology in among the researchers, consumers, and enterprises. The conversational AI powered by natural language processing and machine learning is in the center of AI revolution. So if you see that a lot of AI new, let's say, path-breaking events that are happening, or let's say research that is happening, many of these encompasses the concept of natural language processing and machine learning, and conversational AI is one among them, and it heavily is based on the foundations of NLP and machine learning. By conversational AI, it can be it can appear in many different forms. For example, yes, so I'll come to that. Okay, so chatbot is also a part of conversational AI. It is written here, the most simplest form of conversational system is chatbot. So in conversational AI system, it can be a phone-based personal assistant, then talking to the car, for example, communicating with the robots, clinical uses for mental health treatment, chatting for fun, etc. So all these are the parts of the conversational AI system. And the most simplest form of conversational system is basically this chatbot. Okay, so that was a question, I think. Yes, so chatbot is a part of the conversational systems. So now you see that this chatbot, that why it is important these days, because the market size of chatbot, if you see that from $2.6 billion in 2019 to now, it is $9.4 billion. It can reach by 2024 at a compound annual growth rate of 29.7%. By 2022, most of the banks will automate their services, at least 90% customer interactions through the chatbot. 80% of businesses, they are expecting some sort of chatbots automation, and they have done it actually by 2020. There are more than 3,000 small to medium scale chatbots on different sources. And 50% of the customer these days want that any business actually should be open for 24/7 hours. So if you have a kind of automated system of like chatbot or the conversational system that can converse with the end users, so that can reduce the human effort significantly. That is what is needed. What this conversational AI is supposed to do. So now historically, this chatbot was introduced in 1960, okay, at MIT. Through its, this project was known as the ELIZA. So at that point in time, chatbots mainly was focusing on selecting the response from a set of predefined responses stored in a database or the knowledge base. So for example, if you want to book a, let's say, a railway ticket, and then you have designed a chatbot, and once you have started interacting with the chatbot, so the chatbot, knowledge-based chatbot particularly, it will be able to respond only to a very specific answers which are stored into the knowledge base. But in today's chatbot, if you see that it has become a full-blown industry, and only merely selecting one of the responses is not enough. Okay, so or that from the predefined set of responses. So it is not like merely booking the appointment, or let's say playing a song from a list. So today chatbot is more about human-to-human conversations. So that means when you are talking to the bot should actually understand your feeling. Bot should understand your requirement. So that means if the bot can understand all these human, let's say, characteristics, then the conversations will be more like a human to human rather like a human to machine. These transformations from human to machine communications, so how can we make it more realistic, and how can we make it more human to human like communications, the conversation, is what today chatbot is looking forward. Okay, so all these kind of features, but all these things, for example, making a bot to behave like almost like a human uh, is not possible, is not so straightforward. Okay, so it has not possible, I will not say, but it needs lot of efforts, and it needs lot of things to like, for example, human characteristics can understand. They are very, very dynamic in nature, and the perspective from one human to the other human also get changed. Okay, so that means if you are talking to person A, and then if you are talking to person B, so then their let's say the profilings, their choices, their preferences are not exactly similar. So when the bot talks to person A, it has to follow a particular path. When the bot talks to person B, it has to follow a different path. That as a human being we do. So if you know a particular person, well, let's say if you have many friends, you know that which friend likes what kind of, let's say, discussion with you. And then probably when you talk to them, you actually encourage more, or let's say you bring those topics that your friend will be more interested in. So, and if you can do it, then only these discussions will be more dynamic or more engaging. So, or you feel more connected. Okay, that you always do in our human to human conversation or communication. So can we have all these characteristics to a machine also? So what is needed now, and this has been possible because of these deep language understanding and reasoning capabilities are needed. It should understand the user's need, the context in which the user is speaking, user's mood, then user's personalization, sentiment value, emotional values, and at the same time, it should balance the human-like aspects such as specificity and the empathy. So the specificity and the empathy balancing is very important. That at the, for example, the particular service that you want from the chatbot, that should be served first. Let's say if you are interacting with a chatbot to book a flight ticket, now if the bot is not, let's say, is able to give you that particular service to you, that particular response. Rather, it is showing a lot of empathy to you. Empathy in the sense, let's say, thank you, and lot of good kind of message. So that actually does not solve your purpose. So you have to be, it has to actually provide the specific answers for which you have started interacting with the bot. And at the same time, if the bot is very mechanical, then also you don't feel good. Okay, I'll come to that example, that when the mechanical responses is not very useful. So all these advancements have made it possible. And if you see that Facebook AI, so they have been doing a lot of research in conversational AI, and they have rightly understood or identified 5 different characteristics. And they argued that if artificial intelligence has to master the art of human level conversations, then it has to solve some specific tasks. And what are those specific tasks? The consistency, that for example, that the bot should be able to generate the appropriate responses without any misstepping. There should not be any contradictions, okay, when it is giving some responses. Specificity, generating the very specific response, as I mentioned. Empathy, like the human characteristics, it should understand human speaker's mood, speaker's sentiment values, speaker's emotion values. It should be more polite, okay, in different situations. Let's say in a customer care situation. So I'll show you that why the bot need to be polite. Knowledgeable, that for example, it should be able to acquire the knowledge from the external world. For example, if you say that why 2nd October is important in India, that may not be there in the ongoing conversation. So, but this you can get only from the external, let's say Wikipedia, because 2nd October, you know that this is Mahatma Gandhi's birth anniversary, so it is important. So how do you know that information? So you need some kind of background knowledge, the common sense knowledge, that actually helps the conversational system to generate such kind of responses. And at the end, the multimodal understanding. So not only textual communication, but it should be able to operate with text, image, audio, and video. Okay, so these 5 characteristics it should acquire. And this dialogue systems, or the conversational AI, sometimes we call it dialogue systems or the dialogue agents. Typically, there are two types. One is that open chit chat agents, and then the task oriented dialogue agent. In open chit chat, there is no any specific task. Okay, rather it is a kind of chit chat kind of conversation. So let's say it is not very well defined set of tasks for which you have bid. Okay, let's say sometimes you are asking questions about, let's say, movie rating. Sometimes you're asking about airline reservation. So it is very kind of open-ended kind of conversation. You can ask any kind of questions. So it is very difficult to deal with. Whether in task-oriented, you have designed your model in such a way that it can actually perform very specific tasks. Let's say a chatbot for the railway domain, chatbot for, let's say, mental health care, chatbot for example, the judiciary domain to help people. Okay, chatbot for some, let's say, banking sector. So for the customer interaction. So you know that the task is well defined, and then you have to develop the dialogue systems for it. Okay. So typically in a conversational systems, if you see, there are it follows this kind of cycle. So the path, if you are if your model is a speech-to-speech level communications, that means you are asking a questions. So that is a audio. You have to do the audio processing. Then there is a automatic speech recognitions. Then there is a textual, let's say, textual output here. Then we have this natural language understanding. And this natural language understanding, again, will go to this dialogue management. This dialogue management is natural language generations. Okay. Then it will be a kind of text again. And then there is a text-to-speech synthesis. So you see here, that automatic speech recognitions, then natural language understanding, dialogue management, natural language generation. So these are the three important components for any dialogue system. So this natural language understanding deals with understanding when the speaker has spoken, okay, that it is known as that intent understanding. So you have to understand the intent behind the questions. Then the slot feeding, you have to understand that what kind of slot is to be filled in. Semantics, for example, in case of dialogue management, then you have to do a kind of, let's say, control of the dialogue flow, that in which directions you have to go. And in NLG, actually you have to generate the appropriate response so that it is more acceptable to the speaker at the end. And these first two parts, like automatic speech recognition, because you have to, this bot will have to understand the human speech. So for that, this module is needed. And then finally, this text again will have to be converted to the audio. So for that, it is text to speech synthesis. So this whole cycle, as you can see, that this is a part of any conversational system or a dialogue agent. Now, in my discussions today, I will mainly talk on this part, concentrate on this part, natural language generations, and typically what it can do is that in a kind of end-to-end setting, we'll discuss mainly the deep neural network-based methods, and we'll see some interesting use cases, okay, of empathy, knowledge grounding, personalizations, etc. So see that this natural language generation, so there is a connection with the dialogue management, okay? And the task of the dialogue management, that is the previous module that comes before the natural language generation, is basically known as the content planning. That means what to say in response. If the user has spoken something, asked something, what should be the possible answers, okay? And the generation is how to say that. Okay, so that is generation. But what to say, that will be, you may have multiple options to say. Okay, so this part will be managed by a dialogue manager. So for example, if the user says that book a flight from Kolkata to Delhi, the system will say that, okay, can you please specify the date of travel? Then again, the user will say that, okay, I want to travel this date, and again, there will be a few options, and again, there will be a continuous interactions will happen. Okay, I hope you have understood now the basic things of conversational systems or dialogue systems. Now let's see the very specific part, that what modern days conversational AI is looking for incorporating the specific characteristics. One is that empathy. And what do you mean by the empathetic conversational AI? Let's say this is a speaker, and he says that, okay, I finally got promoted today. Now, if the bot, or let's say, says that why would anyone promote you, then the listener, the speaker will not feel good, okay? And this conversation will not continue for a long time. Reason that because this bot, or let's say the listener, maybe a friend. So that also happens in our day-to-day communication. So let's say you say person B or person A as your good friend, if that particular person understands your feelings very well. When you are successful, if your friend, if that person is acknowledging that, if you have failed, if that particular person is giving a kind of, let's say, consolations, is still stood by you, then only you feel that, okay, that person B is really connected to you. So that way you make your friendship. Let's say your family members, okay, your parents, for example. Why you are so much connected to them? Because of these reasons only. Because they are, so the friends, your friends are only those people who can be at your bad time and good time. So now let's say we want that friend is like a bot here. Now in this case, the person has been promoted, but the bot is responding like this, and the person will not feel good. And this is not going to continue for a long time, this conversation. But if the person, if the bot responds like this, that congrats, that is great, then you see that the person is actually feeling very nice because the bot is acknowledging his achievement or the promotion at the work. And so these conversations will continue for some more time. Maybe after that, the person can say that, okay, when we are meeting or something like this, some more conversation will continue, okay, in real life. So you see that in this case, the conversations will continue. And this kind of conversations, we can say that features or the attributes we want to incorporate into a chatbot or a conversational system. And this is what we mean by introducing the empathy into a conversational system, because here the bot is able to understand the speaker's sentiments, the speaker's emotion, the speaker is happy. And why the speaker is happy? Because he has been promoted. And this understanding makes the bot to respond in a different way. And so these conversations will be more engaging. This is what what we mean by this empathetic conversational AI. But there are a lot of challenges. For example, the emotions can be more than one also. So for example, if you say it is amazing, I am thrilled you got promoted. So here you see that there are two kinds of emotions are expressed. One is the surprise, or the other one is joy. So sentiment and emotion are very closely related. Emotion is more fine-grained. So in this case, uh, joy is more, okay, surprise is less. In the second case, you see that anger is more, acceptance is low. But in the third case, you see sadness is more, fear is less. And what are these values? These values denote the intensity. Okay, that intensity of a particular emotions. That how intense is the emotion. So if you say it is surprise, how much surprise is the person? If you say it is joy, how much joy the person is? If the person is anger, how much angry the person is? Sad, how much sad is they? Understanding this is very important for the bot to react. So if you know that okay, the person is severely in a fearing state or very sad, then the bot will have to generate a response that will specify the situations a bit, that will give a kind of, let's say, let's say, counseling or consolations kind of statement to that particular speaker. So in reality, when we have our when we talk, we have or we when we in many times we have more than one mental states. Okay, and this particular incorporating this kind of situations was not so easier. So and in one of our work that I will discuss, we had incorporated that while the bot has these more than one emotional content, okay, uh, underlying in the user's spoken utterance, how the model will respond in this situation. So this we had introduced this new task for, and we call it as the multi-emotion controlled dialogue generations. There are other works, for example, sentiment understanding whether the positive, negative, or neutral kind of behavior is also important. Okay? And because this emotion and sentiment are very closely related tasks. And particularly in the e-commerce setting, in the customer care situation, the sentiment awareness is very important. That how the bot will understand the sentiment of the speaker. So emotion and sentiment, you can say more or less they are very much closer to each other. And the knowledge grounding is another factor that I mentioned. So in grounded conversation, yes. So sarcastic is also possible. Yes, sarcastic is also possible. Uh, we are mainly discussing now with the emotion and the sentiment, okay, and the knowledge grounding. So knowledge grounding is to incorporate the external knowledge, as I mentioned, that how efficiently you can get some information from the common sense knowledge source, the background knowledge, and incorporate that into the model. So all these need deep understanding of the user's intent, that what users want to speak up. Then the context of the user is very important. Understanding the mood is very important. And ultimately, it will be the awareness is important, that and relatability is very important. So you see that the intent understanding, that means when the speaker speaks, what is the underlying intent behind it? In which context the speaker is speaking? That context, because it is a long dialogue. Dialogue is a kind of ongoing conversation. So suddenly, if you are angry, so there might be a reason. Okay. So there might be a context. So you have to understand the context, then understanding the mood. And if you can do all these, if you can understand the sentiment, emotion, if you also have the external knowledge, if you are able to capture the intent properly, if you can cover the context, then ultimately your conversations, the chatbot, the conversational system will be more aware and relatable. Okay. So the other work that we have done is we'll discuss in details is how to incorporate the politeness and the personalizations. Okay. So by politeness, why politeness is important? In many situations, let's say typically in a customer care, the politeness is an important factor. Okay, I'll give you some use cases. So you are conversing, let's say, if you are not, if you are suffering, let's say, from the bad connections in your particular mobile service, you can reach out to the customer care. If the customer care is not listening to your request carefully, then you feel very bad, and then you may disconnect that particular service, and then you may even think of taking another connections. Okay? So you see that in a customer care situations, okay, the bot, if the bot is the customer care, it has to actually behave in a polite manner, okay, to ensure that the customer is satisfied. This is also true for many other applications, like uh, if you are doing a kind of mental health assessment of some person, and if the persons are serious distressed conditions. So when you are talking to that particular person, you have to be more polite. You have to be more empathetic. Okay. Also, in many situations, you will see that if you are talking to an older people, okay, you have to be more polite. If you are talking to a female, you have to be more polite. So these always happen. Okay, so whether a machine can also behave like that, that if the female speaking user and bot will behave more politely than a male when male talks. If the, let's say, the bot when talks to a Japanese people will be more humble than the US people, because the level of politeness in the US and Japan are different. Okay, so you see that when the bot can behave, let's say, depending upon the age information, if the person is very older, okay, then maybe the bot will behave more politely. Is it possible to do? So these are all the challenges of introducing these the humbleness or the politeness factors or the courteousness factors into into a conversational system. And the personalization, as I mentioned, that depending upon all these person, whether the person is an older person or let's say younger, whether female or male, which geographic location the person belongs to. So depending upon that, the personal attributes can vary. So how can he make the bot behave in a more personalized manner? Okay. So that is also another important factor. So in this case, as you can see that if an ongoing conversation, so this is taken from a part where the person was facing some trouble with a particular service, and the person has reached out to the customer care, and the customer care is saying that how can I help? So now this particular response may not be very pleasant to the user. But if the response is like this, we are sorry to see you are having trouble, help has arrived. Once you have added this, then you see that the person who was facing a problem, he or she will be more satisfied, because here the bot or the agent has understood that the person was facing some problem, and at the same time the bot is apologetic because of the trouble that might have encountered. And then also the bot is assuring that, okay, don't be worried, sir. So help has arrived. Now we are there to help you. So you see that if you behave like this, if the bot adds this kind of expressions, then these conversations will be more engaging, and the user will not feel bad. Okay, so because there is a kind of apology as well as assurance, okay, from the customer care. And there are other situations also. For example, rather than saying this, if you say, hey, Christian, I'm happy to help. These are all the Twitter conversations. So I'll refer to this data. It is the Twitter conversations of various customer care of the companies and the users. Okay. So in this case, you can see it is a greet and the assurance. Then let's say in the flight, enjoy your show while flying, rather than say thank you for your kind words, enjoy your show while flying. Let's say the passenger is saying something good about to the air hostess. That okay, thank you for your nice food or something like this. And then maybe the air hostess saying that okay, thank you for your kind words, enjoy your show while flying. So if you say like this, it will be more interesting or the engaging to this particular user. So this is what you want to incorporate into a kind of conversational system, into a chatbot. So this courteousness, the specificity, as I mentioned, that being only courteousness is not enough, because always you don't need to be courteous also. If you say that you are very polite, but you are not actually doing the work that is given to you, that is also very bad. Okay, in human to human communication also is happening. That there are people who always talks very nicely, but whatever you give them never does that particular work. So that will not solve the purpose. So you have to be specific, you have to deliver, and if the situation demands, you have to be polite, you have to be courteous, and you have to be also consistent. That is very important. Consistency is very important. Okay, you cannot be otherwise there will be biasness. You really cannot work in a but differently for the same situation. So it has to be very consistent. So all these are the current days. These are all the factors that I mentioned. These are all the very interesting research directions that today's dialogue systems, today's let's say conversational AI is exploring. Okay, and many of the things are unexplored. For example, politeness, personalizations, these incorporating more than one emotion. So all these are at the research level. Okay, so it is not the case. There has been a lot of research already existing, and ultimately our goal is to make it more human-like and the engaging. Okay, this is one of the work that I was referring to that we had done in 2021 last year. What we did here is that we defined a new task of multi-emotions and intensity controlled dialogue generations. Okay. As this was a new work, and in most of the NLP problem, if you see that whenever you are solving an interesting task, one problem that you always face is that do we have enough data, do we have enough corpus to build the model? So always these challenges you have to face. So we also face this kind of challenge. So we had to create our own data, and this multi-emotion and intensity aware multi-party dialogue data sets. So multi-party is very important because here the communication is not one-to-one. Let's say in a movie scene, for example, we can see that multiple people are speaking. In a meeting, for example, multiple people are speaking. It is not kind of one-to-one communications. So this is a multi-party conversations data set. And then we proposed again these deep learning based mechanisms to incorporate multiple emotions and their intensity. So now let us see that why this multi-emotion generation is important. I already explained it, but again to repeat, for example, let's say in this case that there is a in ongoing conversations, if there is an utterance like, oh my God, how could you treat them in this manner? So here you can see there are two kinds of emotions, surprise and anger. Now, if one of these emotions is left, let's say, unattended, then the whole meaning will be lost, will not be complete. For example, the oh my God, this particular expression is very crucial. Why it is important? To emphasize that the person is angry, okay, because of the user is due to the unawareness of the situation that lead to the surprise emotions. That means maybe you can think that, okay, some guest has come and then maybe the house owner is not at the house. So when the house owner was not at home, maybe he is, let's say, any other person, or maybe some people who was looking caretaker was at the house, and then maybe his guest or her guest was not properly attended. And then when the owner returned, he is asking that, okay, oh my God, how can you treat them in this manner? So the person is very angry, at the same time surprised. Now you see this, oh my God, this whole expressions, this particular expression is very important. If you only say that, okay, oh my God, that is also not very, let's say, surprising. But if you say, oh my God, that means you are more surprised. Okay. So you see that only writing my God and oh my God, they are different things. So now, so if you take O separately, take it out from this whole expression, then actual meaning, the situation, okay, that actually has caused this surprise as well as the anger, will not be expressed properly. So this is what, because the person is so surprised that ultimately that leads to anger, because there's something that has happened that is not accepted. And if you say only my God, oh God, how could you treat them in this manner? So in this case, the anger expression will not be more. But if you say, oh my God, how can you treat them in this manner? You see that anger is more now. So this kind of behavior we want to incorporate into the conversational model. Okay. And why the intensity now, when it comes that one emotion also can be expressed at the various levels of their intensity. So for example, if you say, it is amazing, I am thrilled you got promoted. Now in this case, the surprise is low, joy is more. In the second case, you can see the sadness is more, fear is low. In the third case, acceptance is low, fear is more. Now, under this kind of situation, so if this is, let's say the speaker is saying, it is amazing, I'm thrilled you got promoted. So now, in this case, you see that the bot is actually responding to this particular person, okay? Or the bot is saying that I am sorry, this could be an infection or cancer. So now, let's say it is a multi-party conversation. So if this is spoken to a particular person, and then what the other person should respond under this particular situation. So this controlling, this kind of understanding actually we should have. That the model, the system should understand that the speaker has been promoted, and so he needs a kind of appreciation for that. Okay. In the second case, the person is sad. Okay. Because there is a kind of let's say cancer infection, so he needs some kind of, let's say, some kind of you have to control that particular situation. So this actually, all these phenomena we want to introduce into a conversational system. And then we had built this model, okay, that shows that you see that here this particular part is we call it as an utterance encoder. That means if there is a dialogue continuing, so every sentence, let's say you are speaking something, that forms that is known as an utterance. And then the bot can respond, that can be a system utterance. So one is the user utterance that you are speaking. In response, whatever bot is saying, that becomes a system utterance, or system response also you can say. Now all these utterances will have to be encoded. And for the encoding purpose, we had used a bidirectional LSTM, a recurrent neural network. Okay. And then there is a context encoder. So what is this context encoder? Because it is a ongoing dialogue, so not only the current utterance understanding is important, rather you have to also understand the whole background context. Okay, what are the context behind it? That means if you are, let's say, nth utterance in the conversation, so what you have spoken earlier, that also will have some kind of influence. Let's say if you are discussing something with your friend, or let's say you are interacting with a bot, for example. So when you start talking, and then let's say after 5 minutes, after 2 minutes, whatever you are saying, so that may be related to the first utterance, okay, that you had spoken earlier. That also happen in our human-to-human level conversations. So previously, whatever has been the history during the conversation, everything should also be known at the current time. So that is encoded by this context encoder. Okay. So again, this is a bidirectional NSTM that takes every utterance of the dialogue and then encodes this utterance level representation. And then again, there is another layer of LSTMs, bidirectional LSTM, that actually takes all these individual utterance representations and then combine them together. Okay. So that means you have to encode the current utterance, you have to encode the whole conversational context, and then we have these two parts of the network. One is that implicit memory and then explicit memory. Now this implicit memory controls that is how much of the emotional content has been expressed. For example, in the previous example I was showing, oh my God. Now let's say this part of the memory will have to control this implicit memory, that okay, in the expressions, oh my God, let's say whether my God has been already generated, O is still left to be generated. Or let's say O has been already generated, how much is left out to be generated? That means O is already generated. Now what next you have to generate? Maybe my God you have to generate. Okay, so oh my God, this is a kind of whole expressions. And this implicit memory is important to control this kind of generations. Okay. Then we have an explicit memory. In case of explicit memory, what happens is that in this case of implicit memory, you see here that this is the current, it is a kind of encoder-decoder model, because encoder takes all the dialogue history and the decoder generates a response. This is what typically is done in an encoder-decoder setting. So in this case, this is the current decoded words that you are generating. You see that this depends on this context vector. This is an attention. So attention will give you that at this particular time, when you are generating this particular word ST, decoded word ST, at this point, when you are generating the word, current word, what are among these encoded word, what are among these words is more important? That you have to identify, right? And this attention gives assigns a weight to each of the words in the context. And at this point, it says that, okay, look, that I want to generate this current word. And at this moment, some specific words from the context are more important. And here you see this MT-1, as I mentioned, that up to T-1, the previous time state, what already has been generated. That is also taken care of. Let's say O has been generated. Now the next is mine. Next time T, you have to generate the word mine. So it controls that, okay, that what has been generated, that also is an input. This context vector is an input, okay? And then based on that, it generates a kind of, let's say, this current hidden state, ST. This explicit memory, on the other hand, controls a kind of balance between the emotional word and the non-emotional word. So you see that when the response is generated, if the whole response is emotional content, then it will not be very meaningful. So some part of the response will contain some emotional content. So this explicit memory is actually controlling that how much emotional content is to be generated in the final output. That is what is to be done by this explicit memory. So this is what has been our architectures. And then we have, for the data, as I mentioned, there was no data. So we had collected data for 8 famous TV shows of more than 500 episodes spanning 456 hours. And there is a combination of drama and comedy both. Every attendance is labeled with the emotions, and these emotions these are the emotions that we have used: anger, acceptance, disgust, fear, joy, sadness, surprise. And intensity we had considered in the range of 0 to 3. So these are the details data set statistics, as you can see, from the number of genres, the number of episodes, number of dialogues, utterances, etc. Now let us see from this data that why this multiple emotions controlling is an important task. Okay. So we can see from these data distributions that here in this particular case, that more than one emotions category, if you see that this part is no emotion in the data. Now single emotion is almost 32, more than 32% of the data. But now you see that two emotions, how many of the utterances have more than two emotions, more than one emotion, is also 32, more than 32%. And more than two emotion, 18%. So now you see that these parts, this 32.6 plus 18.6, this part of the data has more than two emotions, either two or more than two emotions. So that means the data itself shows that indeed there is a necessity to control the dialogue systems which should comply with multiple emotions. Because in real data that we have collected, there itself it shows that more than half of the data has either two or more than two emotions. Okay. Then this shows the why our hypothesis is based on the real ground. Okay, you can say. And after building the models, in one of the how good is the model that you have to do the evaluations. For evaluations, there are two ways. Either that there's some kind of metrics are there that you can compute automatically without any human interventions. And there are certain metrics where you need the human oracle. You can say it's a kind of Turing machine, okay, Turing test, okay, where there was a human interrogator, and there were one responses coming from the human, and another response is coming from the machine. And another human interrogator is checking that was given these two kind of responses. And the human interrogator has to distinguish that which is coming from a machine and which is generated by a human. If the human interrogator is not able to distinguish, then you can say that whatever machine has generated is of high quality, because a human expert is not able to decide what is by the human, what is by the machine. So this kind of testing is also needed. Okay, that is through the manual evaluations, the human evaluation, you can say. Now, in case of automated evaluation, the perplexity is one that it indicates the quality of the generated response. Then for the emotions, we had considered the F-score value. Okay. Then for the intensity is a regression, okay, with real numbers. So you have the Pearson correlation coefficients. And there are also several semantic-based embedding score-based matrices like average embedding, greedy kind of embedding, extrema kind of embedding based metrics. So these are all the standard metrics that we had used. For manual human evaluation, there is fluency that checks the grammatical correctness of the response. The model generates some response. How grammatically correct is the response? Relevance. It ensures that, okay, the generated response, whether it is coherent with the dialogue history or not. Now, emotions, it will check that, okay, that whatever the generated response has the emotions. Is it consistent with the dialogue history? Yes or no? Then intensity, that means it checks that to which degree of the particular emotion is expressed. So these are all the evaluation metrics that we have done, and a lot of evaluations we had carried out. You can see at our paper if you are interested. But what we need at the end, so look, let's see this kind of example. What kind of example is to be generated from the model? So from a conversational history, let's say this is a dialogue. There was other parts of the conversation. Everything is not shown. Only it is taken apart. And in that part, the speaker is saying that it was an amazing night. You think it looked amazing? Now, these are the different models that we have generated. This is the standard hierarchical encoder decoder model. Okay, so it says that, okay, we are not considering any emotion, no intensity. So the response, the model is saying, yes, I think so. Now you see that in our model, if there is an emotion, joy, with 0.6 intensity, and this is the same conversational history, and then what kind of response will be generated? You see that if it is a joy, and the person has said it was an amazing night, you think it looked amazing. Response of the bot is like this. Yes, it was really fascinating. I enjoyed it. Why fascinating? To express that the joy is having higher intensity. Now let's say the joys have lower intensity, 0.3, then you are joyous, but you are not so expressing your joy. So you are saying that, okay, the same response, now you see that it is how it changes. It is generated like this. Yes, it was a nice night. You are not saying that, yes, it was really fascinating. I enjoyed it. You are not saying that. Then let's say if it is a sadness, for example, with 0.3, low sadness, then the response is like this. I found the night gloomy. Now, if the sadness is very high, then the response will appear like this. The whole night I cried all alone. So more sad. Then, for example, Now they see that there are two emotions now, joy and sadness. And the joy is with 0.3 intensity, sadness with 0.6 intensity. What is the generated response? It was nice, but I terribly missed my friend. Because the sadness is more. So terrible is a negative word. So sad is more. Joy is low. So it was saying it was nice, but I terribly missed my train. But now we just do the reverse thing. Joy is more now, and the sadness is low. Then the response looks like this. The night was really great, more joy, only had a little trouble in finding cab. So now you are saying that, okay, you had a little bit trouble in finding cab because your sad is more. But actually you enjoyed this very much. This is what is that this multi-emotions. It shows that how the emotions and the intensity controlled the dialogue generations, and also how this intensity and the multiple emotions controls the dialogue generations. Okay. So then the other work that we had done in 2019 that I was discussing at the beginning, that how can we make a bot more polite? From the context, no, you have to get the context from the history itself, because you have to know that what is the ongoing conversation, and from the ongoing conversation only you have to understand the context. Okay. So this particular work, we had tried to make the bot more courteous particularly in the customer care situations. And I hope you have understood already that why we want to do that. Our goal is to convert a generic chatbot response into a courteous response or the polite response to make it more engaging. As a domain, we had chosen this customer care conversation from the tweet. And ultimately, our purpose is to increase the customer user satisfactions to build the customer relationship. That is the ultimate goal. Now, there are a lot of theories of this courteousness. So there is a theory of politeness in Levin Brown and Levinson's theory, politeness. And it shows that politeness in one's attitude and behavior towards others. So what is the courtesy? Courtesy is nothing but how actually you behave to a other person. That shows how polite you are. Okay. Then this is very common in day-to-day communications. Okay, because let's say very one classical example. If you have gone to a restaurant and if there is if the meal is not good, then you have complained, and if the manager is not listening to you, and they are saying that, okay, the manager is saying that, okay, you are not saying the correct thing. We serve very good food. If you don't like, then you can go some other places. If this is a behavior from the restaurant manager, then as a customer, you will not feel good. And once you come out of this message may be propagated because your dissatisfaction, you may write in different media these days. You can also spread your information in your network, in your peers, and ultimately you'll see there will be a kind of business loss to that particular restaurant. There will be. But if there is the manager is very smart, so he will understand that, okay, no, immediately after getting this complaint, he or she will apologize to you, and even if it is possible, the manager may not take any kind of, let's say, any money from you. So that means ultimately you get a kind of free dinner or free lunch. That is also possible. So now if we have this kind of, let's say, gesture, the behavior of the manager, then even if we had some issues, the problem with the food at the beginning, but you are more satisfied now because of that behavior, and there is a less chance that you may not say bad things or about that particular student, right? Because the behavior, the manager was polite. You were treated very, very well. The manager was apologetic for the bad quality meal. And so now you are satisfied. So this is what we need to incorporate, let's say, into a model. Okay, that is what we mean by the politeness. And there are a lot of theories of politeness, as I mentioned. It can be a positive politeness, negative politeness. Now, positive politeness means what? Let's say if you are in a meeting, if you are saying something, the other listeners uh, may agree to you, okay, and that you can understand by their facial expressions. Okay, but they will say that, okay, they agree with your proposal. Negative politeness is also possible, even if they are not agreeing. Okay, they will say that, okay, no, whatever you are saying, we don't agree. So you see that expressing the not in sync, that means even if they are not agreeing, but they are expressing this. Can you hear me? Hello, I'm audible? Hello. Okay. So you see that here, the negative politeness can be a kind of behavior where you don't agree with that particular speakers. Okay? But still uh, you are you are expressing your disapproval in a polite manner. And this happens in many situations. For example, as a child, when is asking for parents, maybe they can give some advice. Teachers can give some advice that, okay, you should not do this. Well, the child is asking something, kid is asking something, and then you are saying, no, you are not supposed to do it. So you are disapproving, but you are doing it in a very polite manner. You can give advice. So, for example, something is spoken and you don't agree with, or you are giving some advice. So you are giving advice, that means you are not agreeing with the proposal. You are giving another advice, but you are doing it in a polite manner. So you see that this kind of theories exist where you can be you can express your politeness in a positive manner. You can express your agreement in a through the positive manner. Your disagreement, your advices, you can also express, but you can express through the in a polite manner. These are all the different criteria that you have to consider to build a kind of polite models. Now there can be different kind of strategies. For example, in many cases, if you are agreeing with something, you don't have to be very polite. You are joking with your friends. That is the less polite kind of strategies. You are expressing optimism, less polite strategy. But when you have to be more polite, if you want to express the apology, you have to be more polite. Your thanksgiving, appreciations you want to give, you have to express more polite terms. So depending upon the context, depending upon the situations, sometimes you have to be less polite, sometimes you have to be more polite. Now, when to be less polite and when to be more polite, that again you see are very much context dependent and situation dependent. Okay. So in case of customer care behavior, let's see that what kind of conversations are possible. Already we have discussed it. So just to repeat it, how can we help them? All these colored one is making the behavior more apologetic. In this case, colored one is adding a kind of greeting. In this case, it is a kind of assurance. In this case, it is a kind of empathy. And in this case, it is a kind of appreciation. Now I see that in all these cases, okay, so the behavior is kind of polite behavior, and if you rather than generating these kind of generic response, if this kind of responses are generated, then it becomes more engaging and attractive to the users. So by our model, we wanted to generate this kind of courteous responses. Okay. Again, this was there was no data, as I mentioned. We collected the data of Twitter conversation from Kaggle, but this data was not suitable for politeness dialogue system creations. We had preprocessed this data. We had identified the possible cases of politeness, non-politeness, and then we have actually when we try to find the styles of politeness, there are several factors, as I mentioned, that you'll see that this data, Twitter conversations that we collected is from the different companies, and the customers are from the different geographic regions. So depending upon the different companies, let's say sometimes it is a healthcare companies, let's say mental health kind of service providers. Okay, they are more polite. They have to behave in a more polite way. So you see that depending upon the nature of the service, the companies, service providers need to be less polite or more polite. So when you looked at the conversation, so there are a lot of challenges. One is that this kind of notion of politeness can vary across the companies, across the service provider, across the cultures, across the demographies, etc. Okay, and because of that reason, that you really cannot. So identifying these politeness in the customer care domain is not very straightforward. So it is very hard to model this emotion across the conversations. For example, if the customer is angry, the system needs to specify and apologize. And if they are happy, then appreciate. So you see that the bot will have to understand the underlying emotions, the underlying style, okay, underlying situations, and then we have to, the model will have to generate a courteous response. This is what was the task. So we had, before applying this, developing this model, we applied the clustering because there was no data. And so the whole tweeters, we have actually trained on a sentence encoder. So this SNLI is a standard data sets in NLP for natural language inference from Stanford. And you can use this data for a variety of tasks. So in this case, we train the model of the SNLI corpus and represented every tweets, okay, using these representations. And then we had applied a k-means clustering by setting the value k equal to 300. So we have 300 clusters now. Now each of these clusters, why we have created, to understand, because this is huge data. And there was no politeness. We wanted to understand the pattern in the data. So now from the 300 clusters, then we try to identify some kind of pattern that expresses the politeness. And then we have classified it into 3 different categories. That purely courteous, that means some expressions is only courteous, there is no information. And purely informative. And the hybridization of this. Sometimes maybe the courteousness is also needed, informativeness is also important. So what is purely informative? Let's say if you are saying something, okay, that or let's say if you are traveling to a place and you are asking to the agent or the traveling desk that, okay, is the Wi-Fi available in your hotel? If you ask this. So now here the agent or the customer care or the person sitting in the desk, so he or she need not to be very polite because you are asking for some information, whether Wi-Fi is there or not. So then the customer care will say, okay, the Wi-Fi is available or not available. Depending upon that, he or she will respond. And in this case, you see that this is purely an information seeking utterance. Here, the bot may not need to show any kind of politeness. But for example, all the cases that we have discussed so far, that facing trouble, accessing internet in area, mobile, let's say, is not working, continuously call dropping. So under this situation, the customer care agent will have to be more courteous. Okay. So now, if you see that, okay, it is purely courteous without any information, then that is also not very meaningful. We need a combination of both. That there should be some kind of information, and then there should be some kind of courteousness or politeness. Okay, this you did. Then we have this number of conversations, utterances at the end that we had created, and this is our architecture. In the left part, if you can see, it is a hierarchical encoder-decoder model where this every layer is a bidirectional LSTM that encodes the individual utterances. So you obtain here the sentence representations. All these sentence representation is passed in another bidirectional LSTM. Yes, so this is what is the previous slides. Okay, is there any questions? Yes. Yes, what is the question here? Where did you get the parser here? Here we are not using the parser, but parser, if you want to know, the parser is basically it has to segment the sentence depending upon the certain grammatical category, right? And at the end, it has to generate a kind of tree-like structures. And what this tree represents? The tree represents the set of rules, grammatical rules, okay? And their sequences where you will be used in deriving that particular sentence. Okay, so that is what parser does. So it gives a way to derive a particular sentence from a underlying language, and the language has a grammar. Now every language can, English has a grammar, Bangla has a grammar, Hindi has a grammar. So if the sentence is syntactically valid or not, that is actually checked by the parsers. Okay. So in this case, we have not done any parsing, but annotation without annotators, you cannot really, it may not be very authentic. Okay? So if it is without human intervention, so you can do annotation by system, by training on a different data and testing on this particular kind of data. But that way, the model's behavior will not be better. Okay, because everything is automated. So from the conversation, so what kind of semantics you mean? So semantics means here you see that our goal is to generate the appropriate responses, and the semantics are automatically captured in this kind of models because we are representing every word as a vectors, okay, in the semantic space. We are representing every sentence again in the semantic space in the form of sentence encoding. So when you have the sentence encoding means what? So this is a kind of semantic vector of this whole sentence. Okay, so it is implicitly capturing the semantics. Okay. Cost function can be many different kinds. It depends on what kind of applications you are solving. Okay. So generally, by NLP system means cost function. If you want to do that evaluation metric, if you think, or let's say if it is about your loss function, cost function basically you can say and evaluation metrics. Then recall PCC and F score. In generation, as I mentioned, for example, the perplexity, the different matrices like blue, okay, the F score. These are the different functions, metrics or the cost functions that are used, okay, to estimate the accuracy of the model. If you talk about the, let's say, loss function to implement a deep learning model, then again there can be variety. Cross entropy based loss functions. There can be many other loss functions depending upon your own requirement. I think in our group homepage, I think this code are available. Okay, let me cover it and then probably you'll understand this better. Okay, so let's say this is a sentence encoded representation. So you can get this conversational context vector, and then this context vector you have to pass, okay, through the in the decoder. And in the decoder, you can see that the goal is to transform this generic response into a courteous response. This is what the algorithm I am talking about. Okay, this is a kind of encoder decoder model where you can say this is your encoder part, okay, which is a LSTM. This is your decoder, which is again an LSTM. So this encoder is a recurrent neural network basically. LSTM is a recurrent neural network. Okay. So this transforms this generic sentence into a courteous response. But when it does so, it also depends on what it has seen in the context. So this modeling this whole conversational context is important. And that conversational context vector is also passed as an input here. Okay, that means when S2 is generated, it depends on, you see that what has been generated previously and what it has seen in the context on these two factors. Now, in our case, what we have done is that we have introduced a kind of new, let's say, pointer generator network with reinforcement learning. Okay, so here you see that this part is common, again, encoder-decoder model. This part is additional. That at every point, we try to find out a kind of attention. So these A1, A2, A3, A4, AT, these are the weights of each of these hidden, you can say, each of these hidden representation, each of these words, maybe you can say. That what is the weight of send, what is the weight of us, what is the weight of A, what is the weight of DM. So these A1, A2 to AT are basically the weight of the respective words. Okay. This weight will determine that which words are actually important. So this actually is a context vector. That means when you are generating something, we want to estimate that at that point, because this context vector will change from time to time. So when you are at that point, st at time t, here let's say we want to know that at this point, what is the important words from this particular context. So that is basically is the context vector. Now this context vector also and this conversational context vector together generates the current word. This PGen is a kind of probability distributions, a probability value that indicates that whether the word is generated from the vocabulary or the word is generated from the taken from the context. Okay, if the word is generated from the vocabulary, okay, so let's say PGM, that means you are adding some new words to the response. And at the same time, you can also copy some words from this generic response. If it is copied from this generic response, how much you are copying and something that you are generating new that you are getting from this vocabulary distributions. And these two are actually considered to generate this final response. Okay, so that means here we are deciding what is our new words to be generated and how much we are actually copying. It is a kind of pointer generator. So pointer generator will point to the input and then it will copy from the input something. Directly it will copy from some positions. And there is another part that controls that, okay, you cannot exactly copy the whole generic response. You also have to introduce something new, okay? The vocabulary, from the vocabulary word. So because you have to introduce additional Patia's factors there. So that actually we did. And then you see that again, we had done a lot of evaluation using emotional accuracy, content preservation, etc. We had done human evaluations, and then we had actually had a very, we can say that convincing output. Okay. So another work that we have done is the knowledge grounding. Now let's understand what you mean by the knowledge. Okay. So knowledge grounding means that now in whatever we had discussed, nowhere there was a knowledge associated. So now we are considering that, okay, if the situation demands that we need to incorporate some additional knowledge, okay, from the external sources, then how can we integrate that knowledge? Okay, that is the goal. So here you can see that this is a kind of conversation going on, and depending upon the situation, the conversation can go into different directions. Okay, this is the current attendance. And now here the possible responses. And if the possible responses are like this, then from happy to happy. Okay. But if the possible responses are like this, then there is a neutral to curious kind of transition. This is possible. Now, by knowledge grounding, what we mean is that, so in this case, every utterance or in the dialogue has an associated knowledge from the Wikipedia. Okay, that knowledge actually we wanted to incorporate. So I'm not going into details, but if you have a specific question, because time is short, so I wanted to give you an idea about what is multimodality also. But you can see here that we have a shared encoder. Then we have a kind of emotional classifier. This is a multitasking system. So multitasking does what? It can perform both that one task at the same time. Okay, so our task is to do the emotion classification, and at the same time, our task is to generate the responses. Okay, so this is a shared encoder. So this is the current utterance that hello, do you watch the Netflix? Now the answer in the dialogue is like this: hi there, yes I do very much so. Do you have a favorite player? Okay. Then its response is like this: yes I sure do. I really like Brady a lot as a player, and you? So you see that there is a conversation going on, and these are the different emotional classes. Curious to dive deeper. That means you want to know more. So in this case, when the question is, hello, do you watch the Netflix? So we have a shared encoder. This is a kind of bidirectional GRU, okay, that encodes this. And also the context. That means the whole dialogue context encoding is done here through this response decoder. is an input to this response decoder. And then there is an attention. Okay, so emotion classifier classifies this emotion as a curious to dive deeper. Okay, and what can be the possible response if the emotion is like this? That you want to do. So you are speaking something, you want to know that what is emotion, underlying emotion, and what can be the possible response. So there we had an additional knowledge sources also, the Wikipedia knowledge that we had incorporated. And this kind of consistency loss is a kind of, you can say, loss function that ensures that this emotional classification and the decoded responses, they should be very close to each other. Okay, if it is a curious to dive deeper, then the response should be related to this particular emotion. Okay, that is how the consistency loss is managing. So then we have done experiment with standard data sets, for example, this topical chat data, where you have 8 different broad topics. There are knowledge base, as I mentioned, as a Wikipedia articles, Washington Post articles, Reddit fan posts, and every utterance is labeled with this kind of emotions. So maybe I can skip it. Now, a lot of analysis we have done, a lot of you can see from our work. Okay. So another concept that we had introduced at the beginning is the personalization, right? So personalization, arrival response generation with emotions that we had discussed. Now, what is personalization? When the bot interacts, the conversational agent interacts with an user, it has to understand the person's specific requirement, the person's personality, the particular person's mood, etc. And this kind of features, attributes, are not universal. So they can change over a period of time for a particular person also. And from one person to other person, these kind of characteristics will always change. So what we did here is that we tried to build a persona-aware response generation systems where every individual no, Twitter data into sentence means what? So the whole Twitter tweets only we had represented using this the kind of tweet embedding, you can say, tweet representations. Okay. So the purpose was not to represent as a sentence, rather using the whole tweet as a kind of utterance. Okay. So that we did. Then we have this will make the bot more personalized and that are emotionally driven. So as an example, so what is meant by the persona? You see that here there are 2 persons, and this is the profile of the first person. This is the profile of the second person. The first person says that, okay, as a child, I won a national spelling bee. I have been published in the New Yorker magazine. I am a gourmet cook. I have perfect speech. Person two's profile, person two, I am very athletic, I have a brown hair, I love bicycling, I hate carrots. So you see, it is a kind of Facebook friend when you make some friendship in the Facebook by looking at their profile. Only when it interacts, it has some kind of commonalities in your characteristics, or if you find that there is an interest, okay, or that the communications will be useful in some sense, okay, then only you communicate. So you see, in case of personalized communication, so these are the 2 persona features. Persona specific description is given. So person 1 has this kind of characteristics, and person 2 has these characteristics. Now person 1 is saying that, okay, then they have started interacting. Person 1 is saying, hi, I work as a government cook. Person 2 is saying, I don't like carrots. I throw them away. So now see that the person 2, if responds like this, the person 1 will not feel. And then person one says that really, but I can sing pitch perfect. So you see here the person was saying is appreciating that okay, because person two is saying that person one is a government coup. Okay. And person two is saying that okay, I don't like errors, I throw them away. The person two one saying that okay, really, but I can sing pitch perfect. Person two is saying I also cook and I ride my bike to work. Now you see that this response from person two is not very engaging. So we can also make this more engaging by introducing some kind of emotional appeal. Now, how this emotional appeal can be introduced? So let's say if the person one, person two responds like this, that okay, when person one says that okay, I work as a government cook, and now the person two if says okay, that is a great job, but I don't like carrots, I throw them away. So now in this case, that is a great job. So this particular part in the attendance is giving more satisfaction to person one, because person one is will be more satisfied because person two is appreciating the particular job of that particular person one, right? And then person two is saying, I still don't like carrots, I can throw them, I throw them away. So that is okay. But so you see that instead of saying like this, if the person two responds like this, then it will be more interesting and more engaging. So we have done several works on these personalized conversation generations, and then we have shown that how these generated responses can vary. Okay. So now just quickly I'll show you that what do you mean by the multimodality, the multimodal communications. Okay, so as an example, let's say this one. And here the idea is that again we want to build a dialogue system, okay, that understands the speaker's emotions, but the emotions is expressed through the multiple modalities, not only from the text. So, and why this multimodality is important, you can see here that thanks for putting me on hold, I have all the time in the world. Now here the sentiment value will be what? So generally, if you only take this, consider this text, then the sentiment will be positive because of this word thanks. But actually, the speaker, when the speaker has spoken, the speaker was not positive. The speaker was negative. How the model will understand this? Only from the text, it is impossible. Because text says the thanks is a positive word, it will be positive. So we using text, it cannot do. But by acoustics, you can do through, let's say, if there is an audio available, that when the person has spoken it, then from the audio tone, the variation in the speech tone will give an idea that, okay, even if the person has used a positive word, thanks, but the person was actually negative. From the visual expressions also, if the visual expression is available of the person when he was writing this, that okay, thanks for putting me on hold, I have all the time in the world. Let's say that visual expression is available from the person. Then it will also make, it will help us to understand that yes, the person was actually not positive, but the negative. So you see that this shows, this example clarifies or shows that only the textual input is not enough. Rather, the audio and the visual expressions are very important to understand the speaker's sentiment, speaker's emotions. So this shows that only textual input is not possible. So we build a kind of multimodal dialogue systems. Okay, and we have prepared data. This data is like this. Let's say, we had all these school staff in the basement. So we annotated with both the emotion and the sentiment. The first part is emotion, second part is sentiment. And then this conversation is going on, multi-party conversation. You see there is an image also. So you have to consider this audio, you have to consider this video, you also have to consider this text. And then considering everything, you have to actually generate an appropriate response. This is what the problem is. So you have to look at the current textual utterance, this video, the audio, these sentiment, emotions and sentiment, and then you have to generate this particular response. So this is what is needed in these particular conversations. So we had created data by collecting from 10 famous TV shows like Friends, The Big Bang Theory. All these are the drama and comedy kind of TV shows. We have more than 1,200 episodes spanning 746 hours. And then we have extracted all the subtitles and the transcripts for every episode. We have done a lot of processing so that maybe, and this is what the data statistics is. So you can see more details in the data. Maybe I can skip it. And this data was not annotated. One question was that can you do it automatically, all the annotations? So everything automatically you cannot do, but you can follow a kind of semi-supervised model. So in this case also our data, you can see that huge amount of data. We really cannot annotate this more than 100,000, more than 100,000 utterances we have. We really cannot annotate this more than 100,000 utterances. So we follow a kind of semi-supervised approach. We annotated some part of the data, and then we build a supervised machine learning model. And the remaining data we had tested as a test set, and then got all the levels of emotion levels and the sentiment levels. This kind of semi-supervisions you can follow. So you see that we had manually annotated only 2,000 utterances, and then using 3 different human experts, and their distributions are shown here, that how many of them are joy, fear, acceptance, how many of them are neutral, positive, negative, etc. Then we had considered a feature representations. We had built a lot of models like CNN, bidirectional LSTM, BCLSTM, dialogue RNN, etc. And our model is like this, that it shows an accuracy of this. And now once you build your model, and then you can rest all the data you can annotate. Okay? Accuracy may not be 100%. You can see the accuracy level is 68%. So there are 30% errors up there. Okay. Then you have to do a kind of multimodal kind of modeling. So the modeling is done through. The globe is a pretend word vectors. Okay, so you can readily use it. Okay, so we had used the pretend globe embedding. Okay, so we had not trained globe. So globe is already a trained model. You just pass your word and then you get the necessary vector generated. So in this case, you see that the text part is encoded using LSTM. The video part is through the ResNet pretend model. Again, VGG, through VGG, we have done the audio. So now you have the textual representation, video representation, audio representation. Concatenate them together. So you have textual modality, audio modality, visual modality, and do it for every utterance. So you do it, let's say, for the second utterance now, again you follow the same thing. Then third utterance, again you follow the same thing. So in a dialogue for every utterance you do. And then the context encoder will take all these as an input, and then they will consider it, they'll encode it, this context encoder. Then finally, our model is on conditional variational autoencoder. So it has, again, this attendance encoder, all these multimodal encoder you have to do. Additionally, you have sentiment and emotion values. And we have two different networks, here prior network and the recognition network. Then this prior network will compute the probability of Z is an intermediate representations, you can say. So probability of Z given X, which is an X is a kind of encoded representations. Okay, and the recognition network will consider. So we'll try to compute this Z given this mean and the variance. Okay, so these two networks are used basically, and then their distributions are done. Distance between them is computed using the scale divergence, and finally, a decoder is employed to decode the particular response. So in this case, if you look into the data, we had again done a lot of experiment. Maybe I can skip it, and then we have a lot of analysis. Okay. The other one is important is multimodal dialogue system that we have done in case of e-commerce setting. Okay. So let us consider a kind of shopper, and let's say there is a bot in the shopping, let's say, place. User comes and then interacts with the bot. And this kind of interaction is happening. Shopper says that, okay, hello. Now agent, the bot says, hello, is there anything I can help you with today? Now shopper, the person says, show me some kind of, let's say, sandal or some kind of shoes. And then agent says, okay, agent is displaying that. Then again, this conversation is going on. So like for example, in a shopping, when you go to a particular place, or let's say maybe there is a person to help you, to assist you, and the particular thing that you want to buy, you go and talk to the salesperson, and the salesperson display you depending upon your requirement, and the salesperson always wants to sell his or her own product. That is their business need, basically. So now say the bot has to behave like a selling agent. The bot's purpose is to convince you and to sell you. Okay. So now this interaction is happening, as you can see, it is a multimodal interaction because the person is wants to buy some shoes, okay, and then they're displaying this, and the person also say that list more in the upper material as in the fifth image, and style as the third and the fifth. This we always do. So, for example, he's saying that, okay, look at these kind of shoes, okay, fifth image, style of the third image, okay, and the fifth image. Then again, this kind of shoes are displayed. Again, they say that can you list image of the first result? This now the shopper wants to see more on this particular kind. Then these two are displayed. And the third one now the user again saying, okay, no, I don't like this. Can you show this third one? You see, there is very realistic way these conversations can continue. Right? Shopper can say that, okay, and the third one, and the agent says that display that. Now, how the bot will do this automatically? So here, the one simple thing that we did, and very interesting idea, that in the conversation, always we say like this number, that fifth image, then material, upper material, So some kind of material is a kind of attributes of the product. Now fifth image, that means you have displayed something. Now you are indicating a position, okay, position of that image. So this material, this attributes, the positional information, we wanted to incorporate at the time of dialogue generation. That was our main purpose. And we had developed an interesting algorithm, okay, where we had the model can identify the specific style and the specific type of the product depending upon the material and the positions. So you wanted to incorporate some mechanism. We call this is the attention-based mechanism, and this attention mechanism will be able to. Its main purpose is to capture the positional information and also the material informations about the product. Okay, so for that we introduce a position attribute aware attention mechanisms, and positions is also important, as I can show you. And then we had introduced this interesting idea. So you see that at first we have to represent this text and image both for the user utterance and the system utterance. And everything will have to encode through the contextual encoder, and there is a decoder. Decoder will decode the output. And then we have this multimodal encoder, view from left to right. Okay. Then there will be all these will be the concatenated. You can see this is concatenated. Whatever you are seeing from all the images. So let's say 5 images are displayed. So each of these images you represent, concatenate them together. Then you have to combine them. Okay. So this is what was the architectures, and this is the position and attribute aware attention. Okay. So you see that if you say the direction from left to right, then this identifying this. So you at first you encode this particular utterance. And you also have to see this attribute, and this attribute and the positions you are getting from these positions aware image representations. That means you have the position embedding, and you are saying that, okay, the representation of a particular image. Okay, I have a question, I think. So then we have done a lot of experiment. If you have any questions, now you can ask me. Okay. So, so any question from this? I think there was a question that in this case data sets was this one. Your question is from this one, this data. I think there was a question from this. Before this means this data you are saying? Is it so? Yeah, yes. What is the question? Yes, so is the data set available on because yes, this is available. I think it is in our group homepage, you can see this AI NLP machine learning group of IIT Patna. So all these resources are available. If you don't get, then probably you can write to me, so we can give you. So these are all available. So, okay, feature extraction for multimodality. One is that the very pre-trained model we had used. For example, in case of previous work, you see that audio part was done through this VGG, is a standard model. ResNet is also a very standard architectures, so that are widely used for extracting the video-based features. Okay, VGG is also kind of audio features, and you see that this for globe embedding is the textual one. For Resonate, it is a 2048 dimension features we have used for the video, and for audio 128 dimension. So I think this Resonate VGG are the very standard model you can see. Okay, Resonate is a CNN based on the CNN architectures. What are the questions now? So okay. So can you repeat your question? So I think see while creating own data sets, how tagging was done. Yes, so tagging I explained. So tagging in this case, tagging was for the emotional level tagging, and we had followed a semi-supervised model. Okay, so at first we had manually by human three annotators. We used or asked them to annotate 2000 utterances. Okay, and then use this as a training set, extracted all the features, and build all these models based on bidirectional LSTM, CNN, BCLSTM, dialogue RNN, etc. And then you have computed this kind of accuracy we got. Now we have a test set, and yes, so validity is basically this inter-annotator agreement ratio, right? So you see that inter-annotator agreement ratio is important, that how good is the data. Okay, so we have three annotators. So this inter-annotator agreement you have to compute that how often they agree, how often they disagree. Okay, because each of them is annotating the same data, the same instance. Let's say the first of this 2001, let's say for every each of these 2000 utterances is annotated by three annotators. Okay, so the first annotator annotates 2000, second annotator also annotates this 2000, third annotator also annotates this 2000. That means what is happening now? Now for every utterance, you have three different annotations from the three different human annotators. You have to compute a kind of agreement between them, that how often they agree. Okay, inter-annotator agreement ratio we call. This is a very standard way of computing the agreement between the annotators. So the first one, how often matching with the second one. Agreement for the sentiment emotion task is very difficult. Maybe 70 to 70 is a very good number. Okay, because even if the classification system, you see that its accuracy is 68. So human annotations 70, 75 is okay in this case. It depends on the task, because some of the tasks will be very hard, some of the tasks will be very simple. If the task is very simple, not many ambiguities, then agreement will be higher. But if the task is very ambiguous, lot of ambiguities are there, then there will be a lot of problems, a lot of issues. Okay. Sarcasm is difficult. Yes, sarcasm is difficult. Sarcasm is a difficult task, because in sarcasm also it will be lower than sentiment and emotions. Okay, but if you have video, audio, these kind of features are also available in sarcasm, then it is not so difficult. For only from the text, sarcasm detection is very difficult. But if you have the additional context, okay, it is not very very hard, because in the example that I showed you, that it is a kind of sarcastic cases, right? That thanks for putting me on hold. I have all the time in the world. If you say like this, so thanks is a positive, but implied actual meaning is negative. So it is a kind of sarcasm. So you can say. So this you can get from this audio and video based features, right? That is there. Now I see that we have also doing only for text probably. You have gotten the 56 or you had audio, video also. Sarcasm is a difficult task. No, only text is not enough. So you have to, along with the text, you also have to use the other modalities information. Only for the text sarcasm itself is a difficult task. Okay, that probably you have. Yes, so text based is a difficult. So context only can help. So context is only the features. Okay, that is what is important. So we are working with, let's say, several extensively working on the dialogue systems, particularly. This is one of the projects that we are doing with called as SEBA, an intelligent Indian language chatbot. This is a multilingual chatbot in different languages like English, Hindi, Bangla, Telugu, and code mixed language. Domain-wise, there are railways, healthcare, and judiciary. And we have developed this already for the railways, and we have integrated it to WhatsApp, Facebook, and it is also available via web interfacing. We had this is an imprint to a kind project, and we have WePro as an we are also doing something with the goal-oriented and knowledge-driven neural conversations. Then with other industries also, we are working on natural language understanding, natural language, let's say DSC, intent detection, slot filling, multilingual problem. Then we have natural language generations, etc. These are all the publications you can see. So now, whatever we have discussed, so maybe you can ask me now. So maybe if you have any questions, you can.
Thank you, Dr. Asif. Now, participants, you can unmute yourself, I think. Oh, sorry. A lot of questions.
Yes.
Questions are there. Like one question is how to use the data collected from different sources. Do we need to merge all data or need to train separately?
Mm-hmm. 1 second. Let me see the questions. Okay. So Indian language data. I think the question is Indian language data, right? Is it about Indian language or what kind of language data you're asking? Any data? Sources, okay. How to use the data collected from different sources? Do you need to merge all data or need to train? Okay. So merging is good. If the data, if you know they are very related to each other, okay. So then probably you can and you can merge them together. So you can get good accuracy. But if you say that okay, data is unrelated, okay, then adding them together, combining them together may have an undesired effect. Okay, so always merging may not be a good idea. But there are also algorithms that if you have multiple sources of data to solve a particular task, let's say if I say that conversation generation, there are several data sets available. Okay, multi-word data, multi-logo data, then there are this topical chat data. There are several data sets. Now, if you they were developed for different purposes, different domains. Okay. Now, if you want to combine them, this combination, how efficiently you can combine when you are mixing the different domains, how efficiently you can mix the domains. So mixed domain training. So there are specific algorithms. So it is not so straightforward. And also, if it is related, then probably it is better. But unrelated data, if you combine, that will further reduce the performance. That is a problem. Okay.
Ask one question.
Then I think other questions was okay.
Sir, I want to
Something
ask
to that.
one question.
Yes.
Sir, the annotation part you have taken, which was manual, so that you have taken the annotation over the text label or all the kind of multimodal data, all the kind of data was annotated or only the text was annotated?
Sorry, can you repeat again once again?
Sir, in the for training the data set, you have taken the annotation manually, right?
Yes, we have annotated it manually.
So, sir, you have taken the annotation for the text data or for all kind of information you have taken the annotation?
No,
Like
yes,
for
at the time of
geology, the annotation
in
was
case
taken for figurative language was also taken, for textual also it was taken, and for the audio part also it was taken.
yes, for the multimodality case, we have considered all. Okay, so not only the text part, we have considered when you are annotating, we have also considered the audio, video, all kinds of modality.
Okay, okay. Thank you, sir.
So, any questions? Doctor? All modal data means you are saying that, okay, so text, audio, video that you are saying. So text part, you can see that we had, so this is an interesting question actually, that if you have that data from various modalities, let's say one is coming from text, the other is coming from the audio, and the video, then if you merge all of them together, so that may not be very good idea, okay, always. So how efficiently you can manage, okay, because there can be noise also. It's a audio, there can be background noise. So adding audio may have a bad effect. Okay, so how this data fusion, okay, in a multimodal setting is an interesting topic. Okay, so a noise removal sometimes you may have to do. So typically in our case, what we have done is that in our other research we had introduced the interesting attention mechanism. That attention mechanism finds out, let's say, given a text part, which part of the video to focus more on. To attention, we can identify those parts, the interesting part in the video. Now, given a particular part in the video, which part in the text is more relevant to that part of the video, that we can again get using a kind of attention mechanism. So it is a kind of video aware text attention or the text aware video attention. That means you know the text. Now I want to find out, okay, this is my text. What is the important part in the video? Okay. If the video is given to you, you know that, okay, this is my given video. Can I know that which part of the text is important for this? So this kind of attention, the cross modality based attentions you can apply. No, straightforward way is that mostly people do that, just concatenate the image representations or the video representations, audio representations, text representation, but that is not a very sustainable solution. So always blindly merging the all modality informations may not be a good idea. Okay, so you actually have to have a very, you can say that very, I would say very controlled way, controlled and very systematic way of using the information coming from the different sources. Okay. So any other questions you can ask me. So if you have any other questions. Conversational AI is a very can I extract a context from a document? So context means, so what do you mean by context? Context means what? So context is basically a history we are saying here. So that means under which in a dialogue setting, let's say if there are n number of utterances are spoken, and if you are processing the nth utterance, all the previous n minus 1 utterance is a context there. Now you have to select a useful context that we are getting in our case also. You see that now which part of the context is important that we can get through this attention mechanism. So if you see that in our part also we have seen that
the overall flowchart of the
yes. So for example, you can see here that here. So for example, here you can see that this is an input basically. Now from this input, what is the important part? What is the important context that you have to find out? That we are finding through this attention. That at this point we are creating a vector, weighted vector basically. We are weighting each and every word. Okay, weighted by, let's say, A1, W1, A2, W2, A3, W3, AT, WT, something like this. Now, depending upon the values of A1, A2, and AT, the weights will vary. Okay, so these weights will give you an idea that which part of the context is actually useful. Okay, so we are getting it through the attention here. Okay, so attention means like in a human cognition. So if I give you a sentence to read, okay, and then if I ask you to do, let's say, a particular task, then which part of the text you are more focusing on? If you have a kind of, let's say, human cognition, maybe if it is a 15-word sentences, all the words you don't process at a time. It depends upon, if I ask you to do a sentiment analysis to understand whether it is positive, negative, you'll see that after reading the sentence, you focus more on the words that is of adjective in nature, because that actually is the tells about the sentiment. Will give less importance to the other one. So you see that as a human, we think, okay, we focus our attention on a specific part. The same thing we are trying to do with the neural network using this attention mechanism. And this attention is actually giving you an clue, or let's say about a particular context, which is very important at that point. Okay. Future lab session, yes, we will have this kind of some discussions. We'll also show you that how we have built this chatbot. Okay, so for particularly for this one of our work demo, we'll show you that this chatbot on Indian languages, right? So that project we are doing, that also will show you some kind of demo of this saver for this railway domain. Okay, that we have developed a bot for English, Hindi, Bangla, Telugu, and the code mix of English, Hindi, English, Bangla, English, Telugu, all these language pairs. So we'll try to show you that, and also we'll show you some of the implementations of dialogue generations. That how the model can be, how the encoder decoder model is to be used, how it is to be trained. So we will show you all these details. Okay, as much as we can. Sure.
So I think
Hello?
we have already crossed 6:15, and thank
Is
you.
there any
Asif.
other questions? Hello?
So, to be very honest, Dr. Asif, the questions will
Yes.
never end. So,
Hello?
hello.
Yes, yes. So any other questions you have now? Okay, so we'll meet again. Okay, so at the
Okay.
time of,
So,
I think so.
Asif,
Yeah.
thank
Yes.
you.
Yeah.
Thank you. I think my voice was somehow not getting. I think now it's okay. The microphone had some problem. So
Okay.
thank you. And
Okay. Thank you. Thank you.
so I think again you have one more demonstration session at the last date
Last day, yes. So when it is? It was
on
on
18th,
9th
Friday.
Friday. Okay. 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 We'll
Okay.
do.
Okay. Then thank you
Okay then. Bye bye. Thank you.
and bye. And to all the participants, we will take a 10-minute break. Dr. Akshay is there. Dr. Akshay.
Yes, sir. Yes, sir. So I'll continue after
So
10 minutes.
let us take a break of 10 minutes and then probably you can start.
Sure, sir.
Okay. Okay. Thank you.
Good evening, everyone. I hope I'm audible.
Yes, sir. Yes, sir. Please continue, sir.
So, Ashish, can you share your screen and start? So, JP sir, can you make Vikas? Okay, he's able to do it. Okay. So, the material, the notebook files have been shared with all the participants in the chat box. So,
अच्छे सर,
yes, sir.
मैं आपको co-host बना दिया और विकास कुमार के नाम से 2 लॉगिन है।
I think सर
पहले
विकास
सर
प्रेजेंट
को
कर पा रहा है सर, तो कोई प्रॉब्लम नहीं है उसमें।
अच्छा ऑलरेडी है
हाँ, विकास शेयर कर रहा है
और
इसको।
उसका क्या नाम है आशीष।
हाँ, आशीष भी विकास के ही नाम से है।
अच्छा अच्छा
आशीष, you're not, your mic is mute.
इवन आप ये कर सकते हैं सर।
ओके सर, मैं कर सकता हूँ। ओके ओके सर, यस, थैंक यू।
Am I audible, sir?
Yes, now you're audible. Okay, so you're able to share your screen and you're able to speak, right, Ashish?
Yes, sir.
Okay.
Hello, all right. Okay. So in the today's lab session, we will try to we will implementing a program for text classification, right? So we will utilizing a deep neural network, kind of a specific kind of network that is a recurrent neural network, right? So we'll be using a recurrent neural network for performing a text classification, right? So we will look at various steps that are there that are involved in while applying while performing the text classification, right? So here we are going to perform a task. We have chosen a task that is a text sentiment classification. So for that purpose, so the first thing that is required is that we require a data.
Just one minute, Ashish. Yeah. So before we start, we go further. I request all the participants to download the Python notebook, okay, and then upload the notebook in your collab workspace, and then you create a new collab file, and then you can either type as would be demonstrated to you, or you can copy and paste step by step from the file that has been shared with you. So this way you will be able to get a better understanding and a better practice, or to get better be able to use the demonstration that we are giving, okay, rather than simply going along with what Ashish is explaining. So I hope everybody, at least those who are interested, have downloaded the files, Python notebooks. Okay, so we will just wait for a okay. So I hope that all of you have done that. You're already familiar with how to do that, and now we can go this. Okay, great. Yes, Ashish, please proceed.
Yes, sir. So as I already said that today we are going to look at one of the widely performed text classification tasks, that is sentiment classification, right? So for that purpose, we are going to use the IMDb database sentiment classification data set, right? So we can directly take that data set from the standard website only, right? From their standard repository that is being shared by the Stanford University, right? So in this, the first thing that we are trying to import is the few APIs, right? So here we have said, we have written that import TensorFlow STF, right? So here TensorFlow is a high level API, right? So that is widely used for implementing the wide array of deep learning based models, right? So Here we are importing the TensorFlow, and we are importing TensorFlow by creating it an object, right? So here TF is object, right? So we are creating an object for a TensorFlow. In the same way, we are creating an object for NumPy, right? As a NP, right? So we have already discussed that. I think we have discussed NumPy also, right? So if not discussed, so NumPy is basically one of the famous package with the Python, right? That gives a capability to play around with the array kind of thing, right? So, but as while the default data type is list with the Python, right? But again, okay, fine. So while the default data type is Python list, right? But again, there are certain limitations with the list, right? So we cannot directly perform various array operations with the list, right? So for that purpose, we basically employ NumPy, right? Which gives capability that of the array, right? So here we have imported the object for a TensorFlow and NumPy as a TF and NP respectively, right? So after once that we have imported the various APIs, right? The next thing is that we are going to import the data set, right? So for that purpose, what we are going to do is that, first of all, in the line number 1 here, right? So what we are using that we have provided a URL link, right? That is HTTP that basically points to Stanford University, right? So from there, we are downloading this data set that is present in the compressed format, right? Using the curl command, that is CURL, right? So it stands for curl, that is URL, right? So here we are again providing attribute like hyphen capital of O, right? So the purpose of providing capital of O, right, that is basically allows to download a file directly on your local current directory actually, right? So right now our current, okay, let me run these things. Okay, so this is our current directory, right? So this is space. So right now we can see that there is only one folder, right? That is the name of the folder is sample directory, right? So this is our current directory. So when we run this, so here capital O indicates that this we need to download this compressed data set into the current directory, right? So the data set is going to be downloaded here only, right? So in the next line, that is in the line number 5, so we are again using a command called tar, right? So if you refresh this now, so you can see that we have downloaded the tar.js file, right? So its name, and later on we have extracted this into the folder that name is ACL IMBD folder, right? So here we have 2 different subfolders that is corresponding to test and trend, right? So we have downloaded these folders. So here capital O simply indicates that we are going to download this compressed data set into our current directory. Then later on, we are going to extract it using the tar command. Here X means simply the extraction, extract the file, and F indicates the archive file, right? So now that we have downloaded a file, so next thing is that we can also view this, right? So these are simple command line commands, right? That are basically used for extracting and visualizing the various folders here, right? So here ls, that is a list command, that will list all the that will directly gives the directory structure, right? So in the ACL IMDb folder, we are having 2 different folders, right? And again 3 different files. So it is returning these files actually, right? So again, we can also look into the what are the files that are there in the train and the test and train folder actually, right? So we can see that we are having these files in the test and train folders actually, right? So this is how we can we are going to we can download the standard data set directly from the standard repository, right? Directly using their URL actually, right? Using the curl command and then extracting those data set, and we can also visualize the various directory structures that are there with the downloaded files actually, right? The next thing is that we are going to view one of the file. We can also view few samples in the data set, right? So here we are calling upon the cat function, and we are just passing on the path, that is the main folder, that is ASL IMDb. Then inside that folder we have a train folder, right? Inside that here pause. Okay, so inside both train and test folder, right? We are having a two subfolders, right? The first one is corresponding to the negative sentiment, right? And then the pause indicates the positive sentiment. Of course, for our sentiment classification, the most abstract level of classification is performing a binary classification, right? That is simply classifying a sentiment either as a positive or a negative, right? So here we have two different folders in both train and test folder, right? That is negative and positive sentiment. So we are going to use, we are going to view one of the sample that is there in the positive sentiment folder. And this is just the name of that folder, right? So when we run this, so we can see that this is giving output, right? So whatever the sentence or the paragraph that is there in the this particular text file, right? So it is going to display that. So while performing test classification, so this is the input sample that we are having, right? So we are going to use this sample, right? And regarding these labels, so labels can be identified based on this name of that direct folder actually. So if you are extracting the test sentiment, suppose we are extracting the test sentiment from POS folder, right? So in that case, the sentiment of that level is, text is going to be positive. Whereas if you are going to extract our text from a negative folder, right? So its sentiment is going to be negative, right? So based on that, we are going to identify the sentiment of a different text actually, right? Then again, we can see that in the text, in the train folder, we are again having an extra folder with us, right? So we are going to delete that actually, right? So the reason is that we only require negative and positive folders actually, right? Since in the upcoming slides, as we are going to perform this text classification and going to execute the next commands further on, right? So from there onward, we will be using that this directory structure, right, for deciding the labels for the various text data we are having, right? So for that purpose, we only require the folders corresponding to the negative and positive only, right? So in order to avoid any kind of ambiguity, we have simply deleted the extra folder, that is unsupported folder that we are having with the train folder, right? Now, from here onward, now that we are having a data set with us, right, consisting of train and test folder with us, right? So the first thing is that we need, it is required for any machine learning or deep learning model, that we need to extract or pre-process the data actually, right? So for pre-processing, what we are going to do is that, so as already mentioned that TF is an instance of TensorFlow. Then after TensorFlow, you can see following by the dot operator is a Keras, right? So TensorFlow is basically a low-level API, right, for deploying a machine deep learning models. And Keras is a high-level API that is built on the top of the TensorFlow actually, right? So internally, at abstract level, yes, we are using the commands of a Keras, but internally, Keras is again utilizing a TensorFlow only, right? So that's why we are saying that. Okay, we will come to choosing different hyperparameters, right? So we will definitely discuss those things also, right? So here, okay, as I was saying that Keras is a top level API, right? That is built on the top of the TensorFlow only, right? So from TensorFlow, we are going to Keras, and from Keras, we are importing API like pre-processing, right? And from there, we are importing text dataset from directory, right? So what we are doing is that, so first, the argument that we are going to pass is the train data directory, right? So here ACL IMDb is the root folder, and inside the root folder, we have a train folder, right? So we are going to pass the directory structure to this for extracting the train data actually, right? So here we have taken the batch size equal to 32, right? So you can choose any batch size, right? It's not that there is only one choice of batch size of 32, right? But most obvious choice, most often we choose a batch size that is a multiple of that is a power of 2 actually, right? Suppose we have right now we are choosing a batch size of 32, then again we can also choose a batch size of 64, then 128. So we usually choose a batch size of power 2. So that's the usual technique that usually being employed for creating these models, right? And setting up the various hyperparameters actually, right? So here as we have taken a batch size of 32. So batch size indicates, suppose we have a data set consisting of 100 samples, right? So batch size indicate that if we have chosen a batch size of 32, so out of 100 samples, we are going to randomly pick 32 samples, right? We are going to pick the 32 samples, and once that we have picked those 32 samples from the data set, right, consist of 100 samples, so we need to delete those samples from there out, right? So we are going to create a batch consisting of 32 samples is, right? So if you have taken like if you are having a data set with 100 samples and we have taken a batch of 32, that means we are going to have a 4 different batches with us, right? Each batch consisting of 32 samples. And coming to the last batch that we are going to have. So in the first 3 batch, we are going to occupy 96 samples out of 100, right? So in the last batch, we are only going to have 8 samples, right? So this is what, and the purpose of batch size, the purpose of that, why actually we employ batch kind of batch size in the deep learning is and the machine learning is that we don't want to update the weights after we have visited each sample actually, right? We only want to update the weights when we have visited 32 samples or depending on the choice of the batch size actually, right? The benefit of this approach is that, yeah, the training is somewhat a bit more generalized, right? It's not that key after computing the loss for a one single sample, then going to update the weight, again reading a sample, computing error, and again going to update the weight. So in doing so, it will take a lot many epochs, right? So again, choosing a somewhat larger batch size also helps to in a better and a faster training also, right? Now here we have taken the third parameter is the validation split, right? So you have chosen the validation split as 0.2, right? So that means if in a training data set, if we are having 100 samples, so we are taking only 80 samples for the training purpose, right? And the remaining 20 samples is going to be so next remaining 20 samples is going to be the part of the validation data set actually, right? And we have named it as a subset training. Now here a parameter, there is an argument which is that is seed, right? The purpose of seed is to make the model deterministic. This means that in the neural network and deep learning, many times it is we employ a random argument, right? That is, we are going to generate the values in the random fashion, right? So suppose we have a data set consisting of 100 samples. So let's say we have decided that out of those 100 samples, we want 80 samples to a part of a training data set and 20 samples to a part of testing validation data set, right? So assume a case that we have randomly chosen 80 samples from that data set, and we are left with 20 samples, right? So it is quite easy that since we are only left with 20 samples, so we can directly choose that as a validation data set. But since here what we are doing is that if you look at the second part for the validation part also, here also we are providing the same directory only, right? That is similar to the training part actually, right? Okay, we'll come to the difference between the test and validation. So here, okay, here, see, for creating the test and for creating a training and validation data set, what you are doing that we are taking the sample from the same folder directory actually, that is ACL IMDb train, and here also we are using ACL IMDb train, right? So suppose that if you are using the same directory and we are actually not deleting the samples that we have chosen for a training data set, right? So in that case, when we are actually going for a validation, we are actually going to for creating the validation data set, right? So here, then we start, then we will not be able to choose the remaining samples for the validation data set, right? So for that purpose, what we are going to do is that we are providing the same seed for both the cases, right? So seed is equal to 1337 means that for creating the training data set, the first sample will be the first sample is going to have an index that is 1337. That is sample number 1337 is going to the first sample for the training data set. In the and following this initial seed, we are going to generate the random number. Again, our control is here, right? Again, the random value that we are going to generate is going to start from 1337, and the following random numbers that are going to be generated following this number, right? It is going to be equivalent, that is whatever number, whatever the sequence of indexes or the number of sample indexes that we have generated here, right? Here also we are going to generate the same sample indexes also, right? That is, we are going to make this model somewhat deterministic. So since we are going to imply these sample indexes for collecting the 80 samples from the, suppose we have a data set of 100 samples. So we are going to imply these sample indexes to collect the first 80 sample index into the training set, right? Now here also we are able to generate the same sample index, right? So for that purpose, so we are going to leave the first 80 sample index here, right? And the last 20 sample index is going to be considered for the construction of validation data set, right? I hope this is clear to most of you, right? That what is the purpose of seed here, right? Again, okay, someone has asked about that the difference between a validation and test data, right? So the idea is that earlier we are having only the concept of training and testing data set, right? Where training data set is being employed for training a model and testing data set employed for evaluating the model. But in between, while we are performing a training, right, there is no way to assess that how good our training is going on, right? See, when we are performing a training, right? So definitely the training are performs based on the number of epochs, right? So how much amount of epochs we require that we require, that is the number of epochs that a model requires to be trained, it is not easy to decide upon, right? So in order to evaluate the model behavior while it is training, right? See, the testing data can only be employed to evaluate the model accuracy once the training has been completed. But there is no way to evaluate the model accuracy while it is performing the training, right? That is how good or bad the training is going on, right? So for that purpose, for that purpose only, that what we do is that we employ a validation data set, right? So along with the training, so while training, along with the training data set, the validation data set is also passed to the model, right? However, the training data set is only used for training the model, while the validation data set is used for validating or evaluating the model at the runtime only, or while the training process is going on, right? Suppose we have taken a 10 epoch for our model training, right? So once that epoch number 1 has been completed, right? That is, once we have trained our model for 1 epoch on the training data, now we will use the validation data for evaluating that model actually. That is, whatever the model we have obtained after the epoch number 1, right? And validation data set will give an indication of the goodness or the goodness of that model, right? How good or bad that model is, right? Now, once that we have evaluated, again, next we will again go for training the model for the next epoch using the training data set. Again, we will see the validation accuracy or the loss, right? So this basic, so the usual behavior of training loss and accuracy is that once we have started training, the training loss in general will go on to decrease, as well while the training accuracy will go on to increase, right? This will be the normal obvious procedure observation that you will find, right? In most of the cases where we are applying the deep learning models, right? However, if you look at a validation case, right, a validation loss and accuracy, right? So there you can see that initially we will find that the validation loss decreases, which is somewhat close to the which is somewhat very much similar to the training loss, that is also decreasing. But at one point there will come some point, right, during the training, that your training loss will continue to decrease, right? But your validation loss will start increasing, right? So there comes the point, right? So that this point basically indicates that we can now stop training, right? Because if we continue to train further on, right? So that means what is going to happen is that our model is going to overfit, right? It is going to lose the generalization, right? So that's the only that is what the purpose of validation data set is, right?
Hello.
Yes, ma'am.
seed is 1337 means what will be the last value? I mean,
Okay,
seed is some intermediate, in the order that is taken. And why it is taken like 1337 means what
okay,
is the
okay.
reason and what is the last value that I want?
Okay, about the last value, I cannot make a comment, right? But regarding the choice of 137, it's just a random choice, right? You can choose any value, any value. The only thing is that we need to keep in our mind that whatever the value we are going to pick, right? Suppose we can pick here 512 also, right? It's not that we are only going to choose the 1337. We can choose any value. The point is that if we start with 1337, right? Suppose we have started with 1337, since we are going to use a random generator. So suppose it is going to generate some random value, right? It is going to generate a values in a random fashion, right? Suppose we are generating the values like in this order, right? Suppose we have gone towards the end and we have generated this many values, right? So this is how we are. So suppose we have generated this string of integers, right? So we have generated this the sequence of integers, right, in this fashion. So when we are at the validation part, right, when we are actually collecting the validation data set, so suppose that this continues up to the 100 times, right? Suppose this is continuing up to the 100 times, right? So, sorry. So this is
It is
our
not
100.
in the order. It is not in the order. That is
No, it's not going to be in order, right?
1,
Yes, it is not going to be in order, right? The only idea behind this is that when you are going to collect the validation data samples from this folder, right, from this directory, that IMD train, right? Since we are using the same directory for creating a training data set also, right, and for the validation data set also, right? So when the case is there that we are able to generate the same sequence of integer, right? So what we are going to do is that we are going to take, let's say we are choosing like 80 samples for a training purpose, right? And the 20 samples for a validation purpose. So since in both the cases, same sequence of integers are going to be generated, right? So we will take the first 80 sequence of integer, right, for the training purpose, while the last 20 integers for the validation purpose. So since in both the cases we are able to generate the same sequence of integer, so we are going to generate two different data set, that is training and validation data set, in a non-overlapping fashion, right? That is, whatever the samples we have taken for a training purpose, those samples are not present for the validation purpose, and vice versa. So that is what the logic behind this.
Okay. No.
I hope this is clear to you, ma'am.
Yeah, 1337 here seed first is okay that this sequence is like this. In the second, that is where this subset is validation and first subset is training. So in validation also the seed should be same, that you meant to
Yes,
say.
ma'am. The seed has to be same because we want to generate the same sequence of integers here also, right?
Same sequence is needed.
Yes, ma'am. Yes, ma'am. That is required.
Okay.
That then only you are going to filter out the remaining 20 samples from the
Okay.
data set, actually.
Okay, sir. Thank you.
So this is what the purpose of seeding is, right? Again, we have. Yes, definitely the seed should be less than the number of samples, actually, right? So it has to be less than number of samples. Okay, fine. So after that, we have created, we have been able to create the training and validation split, right? The next thing is that we are going to create the training split, right? So for training data set also, we have taken the, for testing data set also, we have passed its directory structure, right? That is ACL IMDb/test, right? So this is where the test data is present, and we have again taken a batch size here, right? After that, we are going to print this whatever the training that is the number of samples that we have obtained corresponding to each data set actually, right? That is training, validation and testing, right? As you can see here, since in actually we are having a 25,000 samples, right, in the training, in the main training folder, right? Out of that, we have chosen 20,000 files for training purpose and 5,000 files for a validation purpose. Similarly, for the testing purpose also, again, we are having a 25,000 files, and we are going to utilize those many for the testing purpose, right? So here we are, this is the number of batches that we are obtaining. So here we are having a 625 batches, right? So if you divide 20,000 by 32, so we are going to obtain like 625 batches. Right. Similarly, for validation part, where we are having a 5,000 file and a batch size 32, so we are going to have a 157 batches, right? And for the testing data set, where we are having 25,000 files and a batch size 32, we are going to have a 782 batches, right? So this is the overall statics of the data set that we have obtained after performing the data split actually, right? Now, next we can also see some of the samples, right, that we have created out of the batches. So here we are like, we have written a for loop, right? So for loop, we have created a for loop, here text batch and label batch. Okay, regarding the batch side, right? So here, so here what the model is going to do is the, so model is going to extract the sample as well as the corresponding label also, right? So as I have already mentioned, right, since we are using a API with us, right, that is tf.keras.preprocessing.text data from directory. So here what it is going to that, it is directly going to follow that directory structure, that is whatever the nomenclature that we are that is going that has been assigned for those folders, right, that is negative and positive. So these nomenclatures are basically used for deciding the label for these samples actually, right? So if we have taken some sample from a negative folder, right, so that sample is going to assign a label of negative sentiment, right? If suppose we have taken up samples from a positive folder, right, so that sample is going to assign a sentiment of positive, right? So this is how the labels of these various samples are going to be decided, right? So here, as we can see that we have taken the raw trained DS, right? So already here we have seen here that we have created a training data set here, right? Raw trained DS, right? In a similar way, we have created raw validation DS and raw test DS, right? So we have created the raw data sets for our here, right? So we are just going to look at few of the samples that is there in these data sets. So we have called upon the raw trained DS, right? And we have called upon a function. We have called a function called take, right? So the purpose of take is simply to indicate the batch actually, right? So here we are referring to the first batch actually, right? So since we know in these batches, since the batch size of the batch is 32, right? So we are calling upon the first batch, right? In the for the training case, that is raw DS, we are having a 625 batches with us, right? So we are going to call the first batch, and inside that we are going to call the text sample and the corresponding label, right? So here you can see this is the first sample we are having with the that is batch number 1, and this is the corresponding label, right? That is label number 1, right? And similarly, this is the second sample, and this is the corresponding label for the one, right? In a similar way, we can visualize all these samples also, right? Okay, now that we have created the separator of the data set, the first thing is that we need to perform a pre-processing. The general pre-processing that is basically required in the case of text mining is like dropping some of the regular expression that we are using, some punctuation marks. We need to drop these things, right? So for that purpose, again, we are going to stick with the TensorFlow only, right? That is TensorFlow.keras.layer, right? So from we are going at a base, we have a TensorFlow. On the top of it, we are having Keras, and from Keras, we are using a class called layers, and from that we are importing a text vectorization, right? Which is an instance of layer actually, right? So we are calling upon those text vectorization. Again, we are importing few extra things like import string and RE, right? RE indicates the regular expression. नहीं वो बोलो ना बैच साइज रेफर करता बैच number रेफर करता है right. So here we are going to use this particular API that is text vectorization, right, for performing the pre-processing. So what we are going to do is, first of all, we have created a customized function here, right? Because we need to select, because since it also contains some HTML tags like, right? So here it contains HTML tags like opening and closing braces, right, in between BR followed by backslash, right? So we are having some HTML tags with us, right, in the text. So we also need to drop those tags also, right? So for that purpose, we are creating a custom function, right, which we have called a custom standardization and input data. So here input data is the text data, that, right? So what we are having, that is text sentence. So the first thing is that we are going to convert all the sentences in the lower string, right? Of course, your sentence can also contain upper it can be composed of both upper cases and lower cases strings, right? So here all these words are having are some of the alphabets are in upper cases, right? And then so we need to just convert all those convert uppercase and lower case in a single case, right? That is a lower case actually, right? So for that purpose, we are calling upon tf.string.lower, right? So we have an input data that is text sentence data. So we are just converting those into the lower case actually, right? So and storing those into the lower case variable, right? Now after that, we have converted our data into the lower cases, right? So the next thing is that we are going to drop, we are creating a regular expression, right? Where we are calling upon tf.string. String is a function that is defined with the tf TensorFlow, right? And there is a regular replace. So this function is basically used to replace the specified regular expression from the input directory. So here, lowercase, it is your input, right? So from input, we are going to look at this particular regular expression that is within this double inverted comma, that is the tag that is used for with the HTML, that is opening and closing braces inside BR followed by closing brace, right? We are going to replace this, right? So we need to replace this with a simple space, right? So for that purpose, replacing some particular regular expression from a text, we can use the regular replace command, right? So after that, we can we have again employed that is tf.string and regular replace, right? Where we are using stripped HTML, that is here. But since this is being used to drop the HTML tags, right, or commands from the your text data, right? So after that, here this is strip HTML is the input, right? And here what we are doing is that we are collecting all the we are taking on all the collection of punctuation, that is string command, string dot punctuation. It is returning the collection or the set of all the punctuation marks we are having, right? And we are collecting those into a list, right? And we are just replacing those, whatever the punctuation marks we are facing, we are just deleting those punctuation marks, right? So here the output that we are expecting, that for any punctuation mark, right? So here we can see that we have simply deleted it, right? We have not replaced it with any space or any kind of any other symbol, right? We have simply dropped it. Now that we have been able to pre-process our text data, right? That is, we have converted our data into the lowercase. Then we have dropped the HTML tags from the text part, right? Then we have dropped the special punctuation marks and all, right, from your text data. What is required? Then we are going to start creating the neural network model, right? So these are some of the parameters that we have defined. That is max feature. So max feature here indicates that is the number of tokens or the words, unique words basically, right? So maximum unique words that we are going to consider for our vocabulary, right? See, for any text processing task, it's very important that of course the very first task is that we need to create a vocabulary, right? So for that purpose, we are defining that we wanted to collect top 20,000 unique words from the collection of text data set actually, right? And we have defined embedding dimension equal to 128 and sequence length to 500, right? Since our sequence length can vary a lot, right? So here we can see that, okay, we have this first two sentences are quite short, right? Then we have a remaining three sentences. Again, this is somewhat moderate level of sentence with us, right? And then this is somewhat a bit larger sentence with us, right? So length of sentence can vary. So of course, we also need to fix the size of these sentences actually, right? So we have fixed this size to 500, right? So whatever the parameters we are taking here, right? It's just some, it's not that fully optimized parameters we are taking, right? So the first thing that we are going to create a text vectorization layer, right? So we have already imported a text vectorization layer, which is a part of a TensorFlow.keras, right? So what are the parameters that we are going to pass to this particular text vectorization layer is that custom standardization function. So we have already created this custom standardization function, right? So this is going to call. Now here we have passed maximum tokens is equal to maximum features, right? So we have defined maximum features equal to 20,000. Suppose we have a data set, text data set with us, right? And when we have collected all the, and we have collected all the unique words that are there in that text data set. Suppose in total we are obtaining a 30,000 different unique words with us, right? That we have extracted from that text data set. But out of those 30,000 text, right, we are only collecting the top 20,000 text only, right? So while collecting what we are doing there, while collecting those unique words, actually, we are also taking into consideration the count or the frequency that we are observing in that data set, right? So only the top 20,000 frequent words, right? That is top 20,000 frequent tokens are only going to be considered for the vocabulary creation, right? And the remaining 10,000 words, we are simply going to drop, right? So that is what the purpose of max token is, right? And here output mode is we have passed an integer. That means, see, these sentences are actually a string of, these are basically a sequence of strings actually, right? So for what is required for any deep learning model or machine learning model, so this model cannot work directly with a string set, right? So definitely these models requires some numerical values actually, right? So for that purpose, so suppose we have a sequence and we have a string of words with us, sequence of words with us. So what is required? We need to replace these words with a unique integer value, right? That actually that is with a unique integer value, right? So for that purpose, here we have written that output mode has to be integer, right? Suppose I'm saying that my name is Ashish, right? So for example, suppose I'm saying my name is Ashish, right? So this is the sentence I am having right now, right? So the first thing, our model cannot work directly on this string data, right? So I need to convert this into some other format, right? So suppose I'm also considering a different sentence. So suppose hello Ashish, right? I have taken a different sentence. So if I talk about the vocabulary size, right? So here vocabulary means, so here vocabulary stands, so here vocabulary is a collection which stands for like words such as my, then name, of course, is, Ashish, then hello, right? So in total, when we consider these two sentences, right? When we are considering these two sentences, in total we are having a six different words, right? But in our vocabulary, we are only going to have a 5 unique words actually, right? And each of these unique words, we are going to assign a unique integer actually. Suppose we are assigning a unique integer 1 to my, right? Then for name, let's say we are assigning it an integer value of 2. Then for is, we are assigning an integer value of 3, right? For Ashish, we are going to assign an integer value of 4. Then hello, we are going to assign an integer value of 5, right? So for this, that is the first sentence, when we are going to convert this sentence into a string of integers. Now, this sentence is actually a string, sequence of strings, this sequence of words actually, right? So we are going to convert this into a string of integers. So for that purpose, we are simply going to consider this vocabulary that is consisting of our unique words and its corresponding integer value, right? So here, referring to this vocabulary, right? So for vocabulary, we have taken a integer value of 1, right? So we are going to replace one my by 1, right? For name, we are going to assign it value of 2. Is going to assign a value of 3, right? And Ashish is going to assign a value of 4, right? So this is now our, this is now is the, so this is currently going to be the representation for our this first sentence actually, right? For the second sentence, if you look at the hello, so the integer value for hello is 5, and similarly the integer value for Ashish is 4. So this second sentence, that is hello Ashish, is going to be represented with the value 5, 4, right? So this is how we are going to convert sentences into the integer value. So this is what the purpose. So this is what the purpose of this vectorization layer is, right? That is text vectorization, right? So we have already defined a standardized, that is how we are going to convert the sentence into a lowercase, then going to drop the HTML tags, and then going to drop the punctuation marks. Then again we have discussed about like how we are going to fix the maximum token. So we are only going to consider the top 20,000 top 20,000 words or the tokens from the all unique collections, right? Okay, that can be an index also, right? So it's both the things are correct, right? Either you call it a value or index. Basically, it's an index only, right? So here, okay, we have discussed the maximum token. That output mode we have already discussed, that is integer. That is, we are interested in converting text data, that is string of words, into a string of integers, right? And the output sequence length that we have already discussed, that is sequence length is, we are going to fix the maximum sequence into 500, right? Okay. So when we are saying that we are going to set the maximum sequence to 500, right? So in the previous example that we have taken, that is my name is Ashish and hello Ashish. So if you see the first sentence, the length of the first sentence is 4, right? Whereas the length of the second sentence is of only 2, right? So in that case, we can fix the length of the sequence to, like, let's say 4, right? So in that case, while converting the text sentence into the string of integers, so if we are having a shorter sentence, right? For the second case where we have used the hello Ashish, that is having only a sequence length of 2, right? So in order to achieve a sequence length of 4, right? So we can go for perform a padding, right? We are going to use a special symbol that is 0, which is in general reserved for the padding purpose, right? So we can use 0 for padding purpose, right? So either we can go for performing a pre-padding or post-padding, right? That is after hello Ashish, that is the representation that we have obtained for hello Ashish is okay. So the representation that we have obtained for hello Ashish, sorry for that. Fine. So let me write that down. So we have a sentence as hello, right? So we have taken its represent as 5, 4, right? So since we have wanted that the length of the max, it length to be fixed to a 4, right? So there are two different options. Either we are going to pre-pad zeros, right? This is called as padding operation, right? So so we are going to perform the padding, either that is we are going to perform the post padding, or other way we are going to perform a pre-padding, right? These things are essential because most machine learning models require a fixed size vector, right? So for that purpose, we generally try to maintain its fixed size actually, right? So that is what the purpose of this this parameter, that is output sequence. Okay, what will happen if max feature? So someone is asking what will happen if max feature and sequence length is going to be same, right? See, these two variables are not connected to each other, right? So here max features means the number of tokens that we are trying to consider, right? So as we have said that we are considering upon only 20,000 unique tokens actually, right? And however, the sequence length is something that is related to the length of the sentences actually, right? So these two things are not connected, right? Okay, now that we have created a vectorized layer, so right, so the purpose of this text vectorization layer is right to perform some sort of preprocessing. That is, I'm just trying to summarize the things, right? So what we are able to achieve by using the text vectorization layer is that we are going to perform, we can go on performing the uppercase or lowercase conversion, right? For our case, we have chosen the lowercase conversion. Again, we can drop few things from the sentences. That is, we can drop the HTML tags, special symbols, punctuation marks. We can drop those things. So this is what the purpose of text vectorization, and convert the text data, that is string of words, into the string of integers actually. That is required for a machine learning deep learning models, right? So we have done those things, right? Okay, so now that we have covered the text vectorization, next thing is that, okay, so here again, now this okay, so this raw train raw underscore train underscore ds, this data set is consisting of both text data as well as corresponding level. That is, either this text correspond to the positive sentiment or the negative sentiment, right? So here we are going to only extract the text data, right? So for that purpose, we are employed, that is two different functions, that is map function and lambda function, right? So how we are going to interpret the lambda function is that we have written lambda x comma y colon x, right? That means here x and y are input, right? Y, whereas this x is output, right? So this lambda function can be used to create a special kind of function, right? Suppose I am interested in performing an addition. So let's say we have given two different variables, right? We have taken two different user-defined variables, right? And at the output, we are expecting A plus B, right? So we can perform this kind of operation here, right? So let's say if A is equal to 3 and B is equal to suppose 5, right? So the output that we are going to expect from this lambda layer, it is going to equal to, that is 5 plus 3, that is 8, right? So that is how we can interpret the lambda, right? So here initially this raw train.ds, it is actually consisting of both text samples as well as corresponding levels also. That is, x represent the text sample and y represent the corresponding level. That is either positive or negative sentiment. So what we are going to do, what we are performing here is that we are choosing lambda, we are defining a function where we are taking as an input, that is text sentence and its corresponding level, and only giving output as x. That is, we are only extracting the text data, right? So that is what the function of this lambda function is, right? Then again, we have also used the mapping function, right? So the purpose of mapping function is that map function takes each row that is consisting of a text sample and a corresponding level. Map function takes a sample set, right? And it passes to the lambda layer, right? Lambda layer is a special function, right? That works on a single sample at a time, right? The purpose of mapping function is that suppose we are having a sample data set consisting of 100 samples, right? That is 100 text samples and its corresponding levels, that is represented with x and y, right? So what this raw map function is performing, that is the map function is picking up the first sample, text sample, and its corresponding level into x and y and passing it to the lambda layer. Then lambda layer is simply extracting only x. Then again, map function is taking the second text sample and its corresponding level and passes it to the lambda layer, right? Where lambda layer looks at x and y and only returns the second text sample. Then following that, map function takes on the third sample, fourth sample, and so on, right? So this is what the purpose of map and lambda function is, right? Finally, we are going to use the vectorized layer dot adapt, right? So adapt is a function of a vector, this text vectorization part only, right? Here, adapt is basically used to compute the vocabulary, right? So already we have passed few things, right? Like what is the maximum of features that we want. So this will only return a vocabulary of size 20,000, consisting of 20,000 unique top keywords actually, right? So this is how we have completed our pre-processing part. Now, from here onward, we are going to start creating our deep learning models, right? Again, there are two different ways, right, by which we can combine this vectorized layer that we have created here, right? This vectorized layer that we have created, we can utilize this layer in two ways, right? Directly, we can make it a part of our deep learning model, right? Directly, we can make it a part of our deep learning model actually, right? So we will discuss this all things, right? Other way is that we employ vectorization layer for converting text into the string of integers, and then we deploy our deep learning models. Or in the first way, either directly make it a part of a deep learning model only, right? But since we are interested in employing the GPU, so obviously we'll be going for a second part, because first way of employing the vectorized layer does not gives a flexibility of utilizing GPU actually, right? So for since we are going to imply the independent vectorized layer, right? So what we are going to do that, again, we have created a function that is vectorized text. It is going to accept that is text and its corresponding label, and then call upon the vectorized layer actually, right? So vectorized layer, we convert that text, that is string of words, into a string of integers, and this is the corresponding labels that we are going to return, right? So here we have called upon the raw data, that is raw trend.ds. Then again, a map function, as I already said, what map function is going to do, it is going to call upon samples one by one, right? And pass it to the vectorized text function, right? And what vectorized text function is going to do, it will convert that text into the string of integers and will return to the, and it will return to the processed trend.ds, right? So trend.ds basically is composed of a processed data actually, right? Similarly, we are going to do this for our validation and testing data also, right? Now here we have used, again, we have processed the data by employing a cache function and a preface function, right? So the purpose of preface function is that, suppose the purpose of preface function is that we are going to fetch upon few samples and put that function into a cache memory, right? Into a cache, right? The benefit of this approach is that since we are going to execute or run the model based on a batch size, right? So what we are going to do that while the model is training or busy with some of the samples, the previous function does what it does, that it collects the next set of samples that is going to be employed for training the model, right? And the preface data is put into a cache, right? So this is what the purpose of this cache and preface. Okay, so this is what the purpose of cache and preface is, right? So we are just doing these things to to speed up the computational performance actually, right? So while some of the data is there in memories, some of the data is getting processed. Once that data is processed, the data is again taken from the cache, right? Cache data is collected, right? And that is going to be processed. And in the meantime, right, simultaneously, next lot of data is going to be fetched into the cache, right? So this basically helps to speed up the training process, right? Okay, fine. So now here from here onward, we are going to actually create a model, right? So as already discussed, TensorFlow is a low-level API. On that, we have a Keras that is built on the top of the TensorFlow. We are importing a class called layers, right? This is a special class that is defined inside the Keras API, right? That gives a capability to importing or calling upon the various kind of deep learning models, right? That are widely used for creating the deep learning architectures, right? So here, the first line of syntax, right? That is that is input is equal to tf.keras.input and shape is equal to 500, comma data type is going to be right. I'm going to explain all these parameters that are whatever the parameters that this layer is accepting, right? So here, as we can see, we have called upon TensorFlow, right? On the top of TensorFlow, we call Keras, and from Keras, we are calling upon the input layer, right? So here you can see that it is showing some information that input is used to inside the Keras tensor, right? So input, the only purpose of input layer is to let the model know what is the input size, that is the size of the input data that we are going to receive, right? So as we have already seen that the maximum size of the sentence that we have fixed is a 500, right? So here the default size, that size that we are going to assign, that we are going to accept as the input is we have defined as 500, right? Then again we have defined the data type as integer 64, right? So we can so this is basically optional. So one can also highlight the data type of the integers value that is string of integers that we are going to accept as an input, right? So the only purpose of input layer is to only highlight the input dimension actually, right? Now following that, the input layer we have an embedding layer. So this is, so from embedding layer actually the training process start, right? So following next to the input layer we have an embedding layer, right? So in the so the okay so the purpose so the purpose of embedding layer is to
Sir,
create yes ma'am.
this D type int 64, it will be always int 64.
No, one can also go for int 32. See, it totally depends. Suppose because int 64 is going to be, take a somewhat higher amount of memory, right? So if suppose you are having a shortage of memory, so you can also decrease it, right? We can also replace it with the int 32, right? That will require somewhat a lower memory as compared to the int 64 actually, right?
Okay. Thank
So
you.
after your conversion, suppose someday you are running your model, right? And you have initially started with int64, but after you have started executing your model, you find that your model is not able to run, right? And it is showing some error, right? Memory crash or memory insufficient, right? So in that case, you can go on to decrement this value, right? You can convert int64 to the int32, right? So that will actually, even though your data is of int64, it will convert that data. It will that is downgrade it to the int32 actually, right? So that will actually help making the things a bit memory efficient actually, right? So the purpose of embedding layer is to create a dense representation for the different words actually, right? See, there are different ways by which we can represent embedding. So if you remember the first example that we have taken, that suppose hello and Assis, right? So we have taken these examples, and so we have taken hello Assis, and we have represented with like 4 okay, this 5,4, right? And then we have 0,0, right? So suppose this is our input that we have we are taking, right, for our model. We have considered this for model, but again for these words, these inputs are somewhat not that much a single dimension may not be able to fully highlight the semantically equivalent words actually, right? Suppose I have taken the two different words. Suppose I'm saying that king is really powerful, right? And other word like king is really right. So suppose I'm taking two different sentences. So here more or less both these two words are used in a more or less same context, right? So that is the words, these two different words, that is powerful and strong, right? So more or less they are semantically connected, right? More or less they are semantically equivalent actually, right? So if we go by this nomenclature scheme, that is where we are using a single integer for representing these words, right? Suppose we have represented powerful with the integer value of like let's say 7, right? That with the strong with the integer value of 9, right? So again, it is hard to say that both the words are semantically equal actually, right? So this is one of the drawbacks with the this nomenclature scheme, right? So to avoid this nomenclature, the drawbacks of this nomenclature scheme, we basically go with the concept of dense embedding representation, right? Where instead of simply representing this words using a single integer value, we are going to convert these single integer values into the dense representation. That is consisting of a collection of, let's say, we are going to take a dimension of okay, let me write. Right. So this is this is an example of dense representation that you are going to create through the embedding layer. So while implying an embedding layer, the idea is that if the two different words, that is power and strong, are both semantically equivalent in terms of context, so that means these two dense representation, that is these two vectors, has to be very much equal, right? So let's say this can be assigned a value like so when you compare these two values, right? For the first case, we are having representing a powerful is 7 and strong with 9, right? Compared to those two, that case, if we look at this particular case, so we can say that, okay, if we are representing these two words using a vector notation, that is powerful is represented using this vector notation, right? So this is the vector representation for powerful, and assuming that this is the vector representation for the strong. So if we assume these two representations, so these two representations are pretty much close in the vector space actually, right? So that means one can assume that both these words are semantically equivalent, right? So that is what the purpose of embedding layer is, right? To create a dense representation, that is meaningful representation, that is somewhat semantically equivalent if they are in the vector space actually, right? Okay. So the different parameters with embedding layer is the maximum feature. So maximum feature here indicate the number of tokens, and here embedding dimension represents the number of dimensions that is the dimension of those word embedding, right? So in the previous example that we have taken, so here the embedding dimension is 3, right? So however, for our case here, we have taken the embedding dimension as 128 actually, right? And the number of tokens is equal to 20,000, right? So next, we are going to pass the inputs to this embedding layer, right? So this is going to produce the dense representation for the input that we're having, that is the input of that is the string of integers. After that, we are going to imply the dropout layer, right? So the purpose of dropout layer is to create a virtual networks, right? Basically not just a single network, but a collection of virtual networks. So when I'm saying that, what does this mean? Suppose we are having, suppose these are some sort of neurons with us, right? So what happens in reality is that if you are considering a dense representation, so this, suppose one is one neuron, right? So I'm right. I hope you are comfortable with the word neuron, right? When we are actually working with neural network, right? Suppose we are having we are focusing on this neuron. So this neuron is going to be connected with all the other neurons at the second layer, right? So this is layer number 1, and this is layer 2, right? So here first neuron is connected to all the other neurons at this layer, that is all the 4 neurons. Similarly, 2 is also connected with all the neurons here. 3 is also connected with all neurons, and 4 is also connected. The purpose of what dropout says that when I am saying that dropout is equal to 50%, that is here total we are having a total of 4 cross 4 connections, right? That is we are having here a total 16 connections. That is first is connected to all 4, second is connected to all 4, 3 is also connected to all 4, 4 is also connected to all 4. That means in total we are having a 4 cross 4, that is 16 connections here, right? So out of those 16 connections, any given point of time, only 6 connections has to be updated, while remaining 6 connections has to be discarded, right? 6 connections, only 8 has to be considered for updating, and while 8 has to be discarded, right? Sorry for that. So that means benefit of this approach is that this creates again whatever the random connection that we are going to drop, right? It is going to be different in a different epoch actually, right? So the benefit of this approach is that not all the connections are not equally not updated in each epoch, but only few connections. So this basically helps in achieving a better generalization, right? And also avoid the overfitting problem actually, right? So once that we have created a embedding layer, now we are going to imply the bidirectional LSTM layer, right? So Actually, this is a class of recurrent neural network, right? So I hope this LSTM network has been discussed. I hope you know this, right? Why X? Okay, someone is asking that why actually we are employing X after the dropout layer, right? See, whenever when we this is actually indicating that for this layer, that is for the embedding layer, this is the input, right? Similarly, for the dropout layer, this X in the bracket indicates that this X is actually the input for this dropout actually, right? So that's again we have created X here, right? We are updating X here, and again this X is passed to this bidirectional LSTM layer, right? So this X is now input to this bidirectional LSTM layer, right? So here we have defined the bidirectional LSTM. Okay, okay. Someone is asking why it connection, and then again advantage of LSTM, right? So definitely, okay. I'm going to discuss those things, right? So why 8 connection? So see, this dropout value is somewhat chosen based on your expertise in the field, right? It can be taken, it can be assigned any value in the range of 0 to 0.0 to 1.0, right? It's basically a choice of probability, right? So definitely we can choose any value in the range of 0 to 1.0, right? And how we are going to choose this value is depend upon your expertise, right? There is no shortcut rule that how we are going to use that, explain it, right? Okay, now next coming to the bidirectional LSTM layer. Okay, okay, so I'm going to discuss this LSTM and recurrent attention layer in a bit. Okay, I'm sharing the link of the website that I'm following, right? Yeah, I'm sharing the link, right? Uh, yeah. Okay, so I've shared the link. So recurrent neural network is a special class of neural network architecture, right? Which is designed in such a way, right? Which is designed in a way to process the sentences word by word, right? See, whenever we are consider whenever we look at a sentence, so sentence is somewhat a string of words actually, right? We have a long, we can have a longer sort of string of words. So how we are going to process these sentences? So we start reading these sentences. Suppose I am reading here, it is written recurrent neural network have loop, right? So we start reading the words one by one till we reach the end, and after that we start the making of the meaning or the context of that particular sentence, right? So here we start by reading recurrent, which is occurring at a timestamp 1, then neural, which is occurring at a timestamp 2, then network, which is occurring at a timestamp 3, then we have a have, which is occurring at a timestamp 4, then we have a loop, which is occurring at timestamp 5. So the benefit that we get with the recurrent neural network, right? The network first of all process recurrent, right? Then once it has processed recurrent, it is going on to process the next one, neural. While it is processing going to process the second one, neural, it is also going to take the reference of past context, right? Now, when our current focus is on neural, right? So recurrent has become the past context, right? So we cannot forget the past context, right? So while processing neural, we have to take into consideration neural as well as the past context, that is recurrent. And based on recurrent neural, right, combined, we are going to generate the output. Now, when we are at network, again, we have to consider a past context, that is recurrent neural, which is a past context, and the current information network. So based on all the past context, that is recurrent neural, and the current content, that is network, we are going to produce the output, right? That is h of t. Now, when we are at have. So here have is having a timestamp 4, that is recurrent having timestamp 1, neural 2, network 3, and have a timestamp 4. So when we are, that is here x of t. So x of t indicates that is whatever the input that we are having a timestamp 4. So here we are having a time at timestamp 4, we are having a have, right? So we are going to take it as a current input, and here you can see that there is a backward arrow, right? That is coming out of A and again going to the A, right? So here backward arrow indicates the context, right? Context means the information that we have obtained after processing recurrent neural network, right? So we have processed recurrent neural network, and whatever the output corresponding to recurrent neural network, we have obtained. See, here I'm just using a simple words, but again, these words are actually represented via dense representation, right? It can be integer or floating value representation, right? So we are utilizing those representations only. But for the simplicity, I'm just taking as a words actually, right? So when we are at x4, that is at a loop have. So we also consider past context, that is indicated by this loop. So we take both have and the past context that goes into A. Then A processes the information and produces the output, that is h of t, that is h of 4. So this is the output that we obtained after that we have processed recurrent neural network up to have, right? Now finally when we are at have, so whatever output that is ht, right? So this ht again goes out here, right? So again this output goes here, that is corresponding to recurrent neural network have, and the current input, that is loop, and we are going to process, and again we are going to obtain the h of t, right? So this is the condensed representation. However, this is the expanded representation where the same architecture, that is the same, this is basically called a recurrent cell actually, right? So the same recurrent cell is employed at a different time step. See, here it is employed at So here it is implied at a time step 0, then 1, then 2, and 3, and up to 3, right? That is same unit is being implied at a different time step, right? So this is what the this is how the recurrent neural architecture works, right? But again, there are some of the significant problem with this architecture actually, right? Suppose if we take that we have 100 time step with us, right? That is, we have a sentence, and sentence is consisting of 100 words actually, right? And suppose we are at word number 100, right? So we are processing the word at 100 position, right? So while processing word at 100 position, what is we are going to do? We are taking the current word, that is 100 word, and we are also considering the context from the previous words actually, right? That is the previous context that we have generated for the past 99 words, right? So we are, based on that, we are going to produce some output, right? But the problem is that whatever the information that we are having at the word number up to at the initial words position, right? Suppose I have the information that we are getting from the time step 0, 1, and 2, right? That is few initial words. So these informations are not able to propagate to up to the 100 positions actually, right? That is, we are losing upon these informations, right? We are not able to carry over these informations up to the position number 100, right? So we call this problem a vanishing gradient problem, right? Why? Because we are not able to carry upon these informations to the last word actually, right? So to avoid this problem, right? So the LSTM network was introduced, right, in the year 1997, right? But though LSTM was introduced in the year 1997, but it gains the popularity only in the year 2011 and 12 only, right? Only up. So for the couple after discovery in the 1997, for the remaining 10 to 15 years, not LSTM does not receive much of the attention, right? It hasn't received much of the attention, and only in the year 2011 and 12 LSTM network started receiving a lot of attention, right? So this is what the architecture of LSTM network is, right? So it is composed of 3 different gates actually, right? Okay, so it employs gates. So here we are having a 3 different gates with it. That is forget gate, input gate, and the output gate. So I'm going to just brief introduction about gate actually, right? So here we have a CT, right? So it is actually a global memory element. So so it's a definite. So I will try to discuss in a bit fast manner, right? Otherwise, I won't be able to cover the whole demo that I'm interested in demonstrating today, right? So the first of gate is the forget gate, right? So here x of t is the current input that we are receiving, and h of t minus 1 is the context that we are able to see. So the purpose of forget gate is that now at this instant we are having a current input with us and the past input with past context with us, right? So based on these two information, that is current input and the past information, we need to decide that whether we need to carry over the past information or not, right? That is what amount of past information I need to forget. So for example, suppose you are in a whenever you go to a college, right? Suppose for a first lecture you attended a lecture of say compiler design, right? And the second lecture is related to the database management system, right? So once you have finished your lecture number 1, that is related to comparison, and you are into the DBMS class, right? So here the context have changed drastically, right? So there is no relationship between compiler design and the database, right? So when you are into the database class, so you does not need to carry on the information that you have gained into the class of compiler design, right? So that is what the purpose of forget is. If we find that the past information, that the past context is not very much closely related to the current information, piece of information, that we can go on to forget that information, right? Using the forget gate. Again, if that the past information, that is context, is really useful, right? In that case, what forget gate is going to do is that it is not going to, it will not allow to forget the information, that is past information, and will carry over the past information into the future state, right? So this is how the gates are actually allowing to avoid the vanishing gradient, right?
Gates are basically functions, no? Mathematical functions.
Yeah, these are a special function. Basically, these are kind of a neural network layers actually, right?
Yes.
See, this lambda layer, right? So this is a kind of neural network layer with sigmoid activation function. So if you know the formula for sigmoid, so the sigmoid function is responsible for producing a value in the
Yes.
range 0 to 1 actually, right?
Yes.
So if we are obtaining a value of 1, that means the past information is really useful and we need to carry over all that past information into the future step, right? If sigmoid function yields a value of 0, that means whatever past function information we are having, we have to forget that information because that information has no connection with the current information, right? So this is what the sigmoid function is going to do with this forget gate actually, right? Actually, this is the neural network layer. Now, whatever the information that we are going to forget, right? So we are going to update this information to this cell state, right? This CT. So this is actually a global memory element, right? So this actually helps maintain the global memory, right? So whatever the things you have information we want to forget, so we are going to multiply. See, whatever the value we are going to obtain after this forget here, we are directly applying and multiplying, right? So suppose some information is useful and we find its value to 1. So when we multiply it with the value with 1, that means all the information going to forwarded in the network architecture, right? If we find that that is not useful, so that means forget gate going to yield a value of 0 and we multiply with 0 with this CT minus 1, right? So that will actually neglect the past value, right? So that is what the purpose of forget gate is. The next gate is input gate. Now here in the forget gate, we are having only a single neural network layer. Now in the case of input gate, we are having two different layers. One consisting of sigmoid function and other one consisting of hyperbolic tanh function, right? So here the function of sigmoid is again the same, right? That is producing a value in the range of 0 to 1 to decide upon what sort of information from the current time step, right? From the current time step, we need to take upon, we need to take into consideration for the future, right? And the purpose of tanh is that to regenerate the value. See, tanh has the Tanh is a function that produces value in the range of +1 to -1, right? And it is a zero center, it has a zero mean actually, right? So whatever values that we are receiving from the xt and st-1, so we are going to take that value and pass it to the Tanh function, right? So that will produce a good value in the range of +1 to -1, that is zero centric value. And when we multiply with the input gate actually. So this both these layers actually constitute the input gate, right? So whatever output we are going to obtain from the input gate, after the forgetting, after we have performed forgetting, then only we have to perform the inputting, right? See, we cannot perform the input, we cannot apply the input logic before the forget logic, right? First of all, we need to forget the past information that is really not useful, and then we have to apply the input gate to add upon the new information to the global memory element, right? So this is what we are doing here, right? And finally, we have the output gate that is used to decide that what information after that we have performed the forgetting and input gate, right? So what sort of information that needs to be used as the output, right? So here again we have a layer with sigmoid activation function, right? So we are again going to decide upon that how we are going to collect that information and use that information to produce as output. And here again we have implied Tanh, the same analogy, that is it is used to generate a value in the range of -1 to +1 and with a zero mean, right? That is mean having a mean of 0, right? And a variance of plus and -1, right? So we implied Tanh. So finally, this is the output that we are getting, that is h of t, right? So this is the expected output that we are going to expect. So this is what, this is how the LSTM network works, right? Again, so now coming to the model part. So here here the next thing that I'm going to discuss is that bidirectional, right? Okay. Okay, so next is the bidirectional layer, right? So the purpose of bidirectional is that, see, when I'm saying that I'm going to scan the input, so suppose here I've written, we add a vanilla hidden layer, right? One way is that we start from V, then process add, then A, then vanilla hidden layer, right? That is, we start proceeding this sentence from left and move towards the right direction, right? So we call this a unidirectional processing. Other way is that we can also process the sentence from the other direction. That is, first of all, we process layer, then hidden, then vanilla, add, then V. If you ask me that what is the benefit of this, so it also happens in many cases that while we are writing. Okay. I will discuss those things. So the purpose is that while we are writing this sentence, we add a vanilla hidden layer. So it's not that when we have reached to the vanilla, it's very obvious that we are also going to add a hidden layer also, right? So that means in a backward direction, that is layer and hidden, there is some relationship between when there is layer, then layer must be preceded by hidden, right? Or any kind of layer convention, right? That can be either a hidden layer, the output layer, input layer. So that means whenever we are writing layer, that means layer has to be preceded by some other word, right? So it is also important to learn the relationship between these two words also, right? So that's why processing the sentence in both forward direction and a backward direction. So this is what the purpose of bidirectional means, right? That is, we going to process the sentence in both forward as well as the backward direction, right? Again, there is a parameter of 64, right? So 64 here indicates that the number of neurons that we are going to employ at the LSTM gates actually, right? And return sequential true means that for each time step, we are going to produce output, right? See, if you look at this diagram, okay, yes. So here, so we are having a t time step with us. One way is that we process the sequence one by one, and in the last, whatever the hidden state we are having, we consider that hidden state as the complete representation for this complete sentence. Or other way, we can also produce the output, that is H0, H1, H2, that is these are the hidden state. We can also produce a hidden state of the output at each time step actually, right? So when we say return state sequence equal true, that means we are producing the hidden state or the output at each time step, that is corresponding to each word, we are able to produce an output, right? So again, someone had asked like why two bidirectional LSTM layers are applied, right? So this technique is basically called as stacking, and the purpose of stacking is that as we are adding a number, as we are going to increase the number of layers with the deep neural network, right? So the filters are the features are getting refined again and again, right? See, at the initial layers, right? The features that we are obtaining, or the representation that we are obtaining, those features are somewhat the intermediate filter, right? That is, those features are somewhat abstract. Abstract in a sense that those features does not contain a lot many information that are really useful for the classification task, right? But as we are employing a more number of layers, so as the features are getting passed through the layers, right? So what these layers are doing, these layers are processing those features. Again, the features are getting processed again and again. So in this way, we are actually trying to create a features that are highly specific in nature, that is, that can be employed to perform a classification. Yes, actually 64 actually represents the number of the dimension of the hidden nodes actually, right? See, I must suggest, right, in one go, it's not that easy, right? It's hard to get analogy. Okay, let me open one other blog, right? See, this is how the one can interpret how the what those numbers represent with the LSTM bidirectional LSTM layers, right? So assuming that those 70s actually stands for this actually, right? This layer actually, right? So assuming that we have a hidden dimension receiving of 70 input units, right? And the input having a dimension of 32. So we are calculating those inputs, that is yielding an input of 102 dimensions. So this layer is having as already mentioned, this is actually a neural network layer. So this layer is having a 70 neurons actually, right? So here, whatever that dimension is 64 actually, right? So this 64 actually represents this 70 actually, right? So we are having a 65 neurons here actually, right? And so when we pass this 102 dimension from this 65, again, when this is 65, now this has to also 65 actually, right? So there is all sort of arithmetic equivalence, right? So you need to maintain those things, right? In order to perform a different kind of arithmetic operations, right? So here also, if you assume this here we are having 65 neurons, so there again it has to be 65 only. So again, this is going to 97 as well. So when we feed this 97 bit of input to this neural network layer having a 65 neuron, so this will produce an output of 65 again, right? So this has to be 65 also, right? Then we are going to perform element-wise multiplication that will again yield a element of 65 unit, right? So so that 65 actually indicates this only, right? That is with all these layers, right? So here this is the layer with the forget gate, right? Then we have a layer with the input gate, right? So again here we are having at both the layers we have 65 neurons, right? Again, at our output layer here also we are having a 65 neurons. So we have to maintain these things, right? It's not that here we are going to get take 65 neurons, then here we are going to take some other number of neurons, right? It cannot be. It cannot be, right? We have to maintain those things, right? So that is what the this 65 represent. This 64 actually represents. Sorry, this 64 represent, right? So now that we have applied the stacking of the LSTM layers, so the output from this is again X, right? So we are going to feed that to the dense neural network, like consisting of 128 neurons, right? And here we have activation, user activation and slave loop. So in most cases, when we are actually using dealing with the deep neural network, so in the intermediate layers, so the most obvious choice of our activation function is ReLU, right? In the intermediate layers, we cannot directly imply sigmoid activation or TADAX activation function, right? So there are obvious reasons that it can lead to the gradient vanishing problem. So definitely ReLUs can avoid the vanishing gradient problem, right? So for that purpose, in the intermediate layer, most obviously we use the imply the ReLU activation function, right? And then following that, we have applied a dropout, and finally we have a output there, right? So we have here we have only taken a one unit, right? Because we are interested in performing whether the sentiment is positive or negative, right? So here we have used a sigmoid activation, right? So depending on the nature of the problem, we have taken into consideration, right? So again, a problem can be like binary classification problem, like then you have a multi-class classification problem, right? Again, you can have a multi-level classification. So coming to the binary classification means either the sample belongs to this class or that class, right? Either sample belongs to positive sentiment or the negative sentiment. So since here we are only performing a two-class problem, right? So for that purpose, we have employed the sigmoid function. So suppose if we have represented, so in this case, so we are going to represent one of the class with 0 and other class with 1, right? So if we have represented positive sentiment with 0, then negative sentiment has to be represented with 1, and vice versa, right? And yes, ma'am. Okay, so finally, now that we have an output here, so here we are summarizing about our final model, right? That is, we are creating a model instance, right? And we are just providing that here input is the input that we are at. So this is our input, initial input, and this prediction is our final output, right? So this input, this is input, and this is our output, right? So this is our final model, right? And finally, we are providing the other hyperparameters for the model training, right? So here model.compile. So let me compile this model, right? Okay, so okay, let me discuss this model summary first, right? Then I will discuss the parameters with this compile module, right? So as already discussed, so input layer, in the input layer we have the maximum sentence layer 500, right? So here none, you can see there is a variable called none, right? So this basically stands for the batch size only, but basically we don't want to. So it basically stands for batch size, right? So it's so here it is basically 32. But in some cases where we want to have a flexibility, right? So we does not hard code these things, right? So for that purpose, it gives a none. It is similar to like when we don't want to specify the integer type, so we use void, right? It is similar to what that much that thing only. Where we want when we don't want to specify the shape, so it is none. That means it can be any shape, right? But right now, shape is so here this none is basically standing for batch size, right? Following that, we have an embedding layer. So we have taken a sentence 500 length, and we have converted it to a dense representation consisting of say 500 cross 128. So here 500 is a sequence length, right? And this 128 is the dimension of each word, right? So 500. So that means in a sentence we have 500 different words, and for each word we are creating a representation of 128 vectors actually, right? So this is what 128. So this 128, this here we have said xt is equal to 32. But since in our case, so we have taken 128. So this is what 128 is. This xt is 128 actually, right? And this x of t minus 1, this is 64. Then we have applied a dropout. So as I already said, dropout is doing nothing, but it is only creating a set of virtual neural network layers, right? Then we have a bidirectional layer. So here we have in the first layer we have used return sequence is equal to true, right? When we are using return sequence is equal to true, that means for as already mentioned that for each time step, that is for each word, I want to obtain the hidden state vector, right? So we are having a 500 words with us in a sentence. So for each word, we are creating a 128 dimensional vector, right? That is hidden representation. And for second bidirectional layer, right, we're only generating a 128 vector, right? That means, as already mentioned, that there is two different way, right? Either we can only take the last step hidden state as a vector, or we can generate all the hidden state, right? So here, since we haven't mentioned return sequence equal true, right? That means we are only considering the last hidden state vector, right? Again, one more important thing. So here we have passed the number of neurons as 64, right? But here the output we are getting is 128, right? This is because of the bidirectional nature, right? That is, in the forward direction, we are obtaining 64 vector. Then again, in the backward direction, we are obtaining 64. And that's why we are obtaining a 128 dimension feature vector, right? Then again, we have implied dense layer with 128 vectors, right? So this is what 128 is. And then we have implied dropout, and then finally a dense output layer with one neuron, right? So here we during the modular compile, we have passed upon few things like loss is equal to binary cross entropy. Again, it's totally depend upon the nature of the problem we have taken into consideration, right? Since we are here, we are dealing with the binary, like a binary classification. So we have taken a binary cross entropy. Suppose we have performing like multi-class classification problem, then you should have chosen like a categorical cross entropy, right? So this is the loss function that depends. Then again, there is a wider of optimizer. So the role of optimizer is to use this loss, right? So use the loss to update the weight. So this is what the role of optimizer is, right? So here Adam is used as an optimizer. So there are a wide array of optimizers with us, right? In a similar way, we have a wide array of loss functions, right, defined. No, here third parameter is a matrix that is used to evaluate the model performance while it is training, right? And then finally, for this model summary, right? This is going to generate this total graph actually, right? Now again, so here, if I start training, so here I am going to train the model, right? So I've said the epoch number is equal to 5 and the model dot fit, right? So here fit function is used to train the model, right? Accept as parameters, right? So this is the training data set, right? And then we have the validation data set, right? With us.
Ashish, just to
yes.
So I think it's already 8:15. You know, as with it is usual the lab sessions, it is good that people are asking questions. So what we'll do is, so we have one more lab session day after tomorrow. So where we'll be talking about BERT model and this. So when we start, we can also, you know, sort of wrap this up in case you have more questions. So what we would recommend you do is, so you already have the code. You should try running this code on your own. Okay, and see what has been discussed. Try to relate to what Ashish has discussed. And if you have questions, in the next lab session before we start the BERT module, we can sort of wrap this up, okay, and answer the questions. So, okay. So that is all for today. Attendance link, I think JP sir may have shared the attendance link in the afternoon only. Yes, shared code. We have already shared the code in the link. Vikas, can you just copy and paste the code again? The link again, Google Drive link again, chat box. And don't worry, at the end, so we will, the link was shared in this chat box. At the, okay, let me just check with JP sir if the attendance has been shared or not. Just at the end, we will put together all the material and share it again, okay, in one common place. So JP sir will do that.
Sir, one quick question.
Yes.
The batch size 32 here we have taken, and the LSTM nodes we have taken 64. Is there a recommended combination of numbers between the two, or are they like random values that we choose? Batch size is understood, but LSTM 64, is there some thought behind choosing 64 number of nodes for LSTM?
Okay, for most of these hyperparameters now, whereby we are like selecting the number of neurons. So for instance, for LSTM, we are using 64 neurons. For dense layer, we are choosing 128 neurons. So it's
Yes.
more of depends upon your expertise in the field actually, right?
Okay.
On an arbitrary, if you suppose you starting with some random experiments, right? So in that case, you can start with some values that is somewhere in the between of like those small values actually, right? You don't with a very high value,
Yes.
but only with your expertise now you are these hyperparameters can be, because
Got
this is one of the major challenge with the deep learning, right? That how you are going to choose these hyperparameters actually.
I think this is also
Obvious
part
answer
of
to this.
unexplainable AI that we talk
Yes, again, there is no obvious right
Yeah.
logic that how we are going to choose these things, right?
Yeah.
Only after performing a hit and trial kind of thing or grid search kind of thing, right? We are going to decide upon these things.
Thank you, sir.
Okay, so Sangeeta would be sharing the link again. So JP sir said the link has already been shared, but she will share again on the chat box here. And so it was good. It is really good parts to see participation from the audience. Is something which we don't find, to this extent in other FDPs that we conduct. So it is very encouraging and good to see that people are really interested. So thank you, Ashish. You may disconnect.
Okay, sir.
So thank you, everyone.